Hello. Okay, so can you hear us well?
Yes, we can.
Okay, so now we're going to mute everybody on the line. I'll explain the process in just a bit. But for now, everybody's going to be muted just so that we can go on and not hear everybody's noises. And let us know if you don't hear well. Just send an email to myself. So thank you very much.
The conference has been muted.
Perfect. Okay. Speak loud. Yeah.
All right. Thank you very much. Let's start. Sorry for a few minutes delay. We had problem with connection. So this is NGAE's SHAC workshop. As you know, NGAE is a little bit different than other projects because it has science component and formal SHAC component. And under the science component, lots of researchers, they develop lots of various things, but they will be reviewed, all these pieces under the SHAC umbrella, like today and tomorrow. Since last time that we were here, we have made significant progress. The database, Flatfile, various versions of that have been distributed internally, and whoever asked, we supplied the Flatfile for their use. Few peer reports have been published. The peer report on the database has been published and posted at the peer website. Peer report on the regionalization also has been published and posted. Moment area scaling report also published. 2 reports by geotechnical working group, one on reference site condition and one on reference kappa have been published and posted. Much more progress has been done on the GMPE development that you are going to hear today and tomorrow. The actual time series of NGAEs for Central Eastern North America, they are incorporated into peer website for the public use. In early 2015, that will become publicly available, actual time series. The Flatfile obviously is released earlier. I would like to thank the sponsors of NGAEs, NRC, DOE, and EPRI. They supported this project from day one, and we really appreciate their support. I'd like to thank the PPRP members. Very constructive interactions we have had with PPRP members. They provided very good comments, and we like to hear more from them in the next few months. Many researchers and practitioners, especially in the last few months, really, they worked day and night. I witnessed on various pieces, small and large pieces, and I really appreciate their efforts. Finally, I would like to thank volunteers, overqualified volunteers. Mesa is postdoc at PIER, Sahar and Sifat are researchers at PIER, and they are helping us today. Thank you very much for your participation, and now Christine is going to go over the agenda of the meeting. Thank you very much.
Lots of volunteers on this project. Okay. So it's going to be quick, my intro this morning. I'm not going to go over the whole SHAC process, just a couple of slides on that, just to remind you of what we're trying to achieve here. So the NGA's project, it's a science development phase and a SHAC level 3 project. The objective is to develop a ground motion characterization model that includes GMPEs for the median ground motions and standard deviations. We refer to that as sigma, even though there's more than one Greek letter in that definition now. For aleatory variability, we assemble those in logic trees to capture the epistemic uncertainty, and that's for average horizontal ground motions, PSA 5% depth, between 0.1 and 100 hertz, or 0.01 seconds and 10 seconds. For hard rock sites located within 1,000 km kilometers of future events expected in the central, eastern North America and CENA from magnitude 4 to 8.6. So the critical issues in this project, I'm diving right into it. Hazard critical issues are regionalization of source and path parameters, characterizing the geometrical spreading the first 40 kilometers, getting the right stress drop of stress parameter if inside a model, and extrapolate ground motions to large magnitudes. We need to quantify the standard deviation of ground motions because for low probabilities it really drives the hazard, and the quantification of side effects. And for the purpose of NGE's objective, it's really to be able to remove them from our recorded data, so we go to raw. So it's a really important task. Please turn off your cell phone ringers. There's a cavalry coming in this morning. Okay. We're awake. Thank you. Okay, the solution is to run this multidisciplinary science project with working groups focused on specific research tasks. We have had over 50 researchers working in NGE so far. We then build models making extensive use of seismological constraints, so that's the simulation, and we perform the evaluation and integration of those models under the SHAC level 3 umbrella. So that's the solution to address those issues. So this is a SHAC workshop. Those of you who are not familiar with that, well, go read the new reg, please, or listen to previous presentations. SHAC is a set of procedural guidelines for seismic hazard analysis developed by the Seismic, Senior Seismic Hazard Analysis Group. One important component of the SHAC process is to have those formal workshops, and they're developed into 3 themes. The 2 themes we'll have today are theme 2, proponent discussions of alternative interpretations of data, model, etc., and 3, the presentation and feedback on proposed models. So if you saw the header, this is a workshop 2C, so components of workshop 2, but it's the third, and 3A is the first time we address those issues. So it's like that. So the key participants this week are really the technical integration team, so Norm Abramson and I, Christine Goulet, we chair the TI team, which also includes Linda Alatic, Neil Atkinson, Rob Grace, and Bob Young. We have a lot of invited proponents and resource experts. Those of you who are here, there's a list of participants at the end of the agenda with the roles. So we have invited multiple proponents, experts, and resource experts to participate. And outside of that, we have our participatory peer review panel, the PPRP. So this is chaired by Gabe Sorrell, with John Adams, John Abel, Justin Bond, and Rich Lee. In the concept of the formal SHAC workshop, the PPRP is to remain mostly quiet and only provide comments and feedback at the end of the day. We've learned that it works better if we invite them to participate in the discussion. It clears up a lot of issues. July was really successful in that sense because we have really the communication flowing and going. And I think it's important. Beyond just taking the mic and saying, oh, I'm talking as a resource expert, we welcome your comments and because it really simplifies the communication and for everybody. So if it's too much, we'll let you know. Okay, so this is how, these are the people we expect to interact. If you're listed as an observer, so you're not officially allowed, quote unquote, to participate, but at the end of the day, if time allows, you can provide comments and questions, and also in writing as well. Louder? Louder. Man, oh, this is rare. I mean, people don't have to say louder. Okay, let me try this. Thank you. Okay, today's meeting is recorded to be posted online as part of the SHAC documentation, so that's why it's important to speak loudly. So we have over 100 participants in person and online. I ask again, and you guys are so well trained, to please use a microphone and state your name at least the first couple times. People will need to recognize your voices at some point. We're going to try to keep the discussions focused on critical issues and not go on sideways tracks of interesting things that are not critical. Presentations from all the people presenting, please are due before your session starts, so either at the breakfast, lunch, or break, please bring them to Sahar and myself so we can explain them to them. Remote attendees will be muted for the duration of the workshop. I don't want to have too much noise. You can raise your hand in the ReadyTalk app. You can complain that we don't speak loud enough. You can use also the chat function to ask questions, or you can email to myself as well in the invite from ReadyTalk. So the agenda in additional info is in the tier NG page. Does it sound better now? Okay. Brief overview of schedule. So we're here in the SHAC workshop 2C3A. That's now. We're going to have the SHAC workshop 3B in January 21st, 22nd. It's going to be a public workshop, but not as large in terms of attendance in person. We want to limit the number of people, the cost, and this and that. So it's going to be mainly CIT and PPRP, but everybody can join online as always at the public workshop. And we have the project wrap-up still scheduled for April 13th, and we're making good progress. So that's the overall schedule. We have a really very interesting workshop. The next 2 days are really exciting and show a lot of new results, fresh, really fresh. So let's talk now. I'm going to switch gears and talk more about what we're going to cover, the different GMPEs. So the NGE's approaches to candidate model, median instance. So this is part of the NGE scientific development, and it's through the GMPE working group and the Sigma working group. The GMPE working group is new. Sigma working group has been working. So this is basically groups of model developers. It's open to the TI team, and the PPRP can listen in. The GMPE working group started to have weekly calls since August, and it's been working well. The goal of these groups is really to foster collaboration, share all the data, openly discuss alternate approaches and interpretations, and that's where people throw in new ideas on how to do. There's a lot of intellectual, interesting discussions. So there's been really a rapid progress since the last workshop, and some of it. As part of the SSHAC process, the TI team tasks are really to evaluate, considering all data, models, and methods relevant to hazard analysis, all those different components that are proposed by the larger technical community, and then to integrate, so to represent the center, body, and range of the technically defensible interpretation, the CBR of the TDI, in light of that evaluation process. So the focus of this workshop is really going to be more on seeing what has happened within those working groups in terms of performance models, but this serves as part of the process of the evaluation validation. Okay, so there's a lot of information in here. These are the GMPs that will be covered in this workshop. So we'll start with the median. I'll have the approach, constraints, how the extrapolation is made to larger magnitude, and all that, and the presentation. So there's the traditional point source stochastic. It's modeled in FAS space, oriented to spectrum space. The constraints can be different depending on the specific models, but I'm listing here those that we're going to look at. Point source model is the underlying assumption that there's a source spectrum, usually blue. How come the sound is different? Can you lower it? Oh, the phone did okay still? This is weird. Okay, I'll talk to him. Yes, it did. Oh, I found that the phone was out there. Really? Okay. Thank you. Upstairs. Okay, so then the other constraints are, so right at, you know, this is really a pain. So why don't, up there, the booth, you say that the phone is fixed now? Oh, okay. No. Okay, it goes, but it's not. Yes. We can't hear you, there's no microphone. Yes, I'll repeat it. So John is asking for a copy of this table. Yes, I will share that. I'll put it on the website today. You can download it. Okay? Go to the event today. Okay. So yes. So traditional point source stochastics, SES-based approaches. There's two that we'll consider. So one is to consider again on the point source model itself, published sets of empirical Q, geometrical spreading, duration, etc. And the CENA motion has constraints as well for fitting. The extrapolation is done with the point source model, and we'll have an SM suite of models. Is it better than that or what? Okay, so that should be good. So people, you'll need to talk into my phone. Sorry. So Dave Bohr will present is SM Sim suite of models. Okay, another one is going to be that's more again point source, but based on broadband inversion of CENA ground motions to define the parameters. Again, extrapolation with the point source, and that's going to be the suite of models presented later today by Bob Dara. Then there's this new category that I put basically the title of the approach because it was difficult to summarize. It's also a point source model, but it's called Regionally Adjustable Generic GMPE based on point source model. I renamed that Point Source Reference Empirical, so Gail maybe can propose a nice name, but the idea here is that the point source model is used to develop a generic GMPE. The parameters are defined for data-rich host regions, so Western US, for example, and the adjustments are done using the CENA ground motions. So the extrapolation is done with that adjusted generic GMPE. So Emra Yenye is going to present that today from Yenye and Atkinson. We have the hybrid empirical approach. This is FAS and PSA based because it uses both approaches. So they use published sets of CENA and Western US point source models, and they tailor them and adjust them. But then they use a GMP in the host region where there's a lot of data from Western US to do the extrapolation. So that's the approach by Pezeshk et al. It's going to be presented. There's also the fully finite fault simulations-based approach. That's this one is PSA-based, and the constraints are the finite fault model itself and the CENA ground motions, again, for fitting and adjusting. The extrapolation is straightforward with the finite fault model, and that's going to be presented by Frankel. We have the traditional empirical PSA-based, so that's what a lot of people are used to. So you use the CENA ground motions where you have data. And then for the extrapolation, you can use different approaches. You can use the finite fault simulations, the point source simulations, or intensity data. We have two sets here. Al Norman and Kramer will present their GMP based on intensity extrapolation. Grazer, I think his intent is to use the finite fault simulations, but we haven't shared those results yet. We just got them off very recently. So he can clarify that in his presentation. Then there's the referenced empirical, that's PSA-based, so again, using the CENA ground motions and using the GMP host region, Western US, and adjust that. So Asani and Atkinson will present that. Then we have this new approach that will require a bit more time than the other ones because it's newer and it has more pieces. It's the peer proposed model. It's a FAS RVT PSA empirical. So it requires a Fourier amplitude spectral model and a duration model. It's constrained on the CENA ground motions, but then the point source and finite fault models are used for scaling and extrapolation. And the global ground motions are used for extrapolation of the duration model for those larger magnitudes. So that's what we call the peer suite, and Justin Hollenbeck will present that for us. Then in the sigma, we have the equivalent. I called it the reference empirical. This is PSA based for sigma. Then when I say sigma, I mean sigma, phi, tau, phi SS. So that's just the standard deviation. And basically we use the CENA ground motions where we have them, and then we tie that into the global ground motions data set and use those for extrapolation. That's also a peer suite that Linda Alatek will present. So we may rename and tweak these things. I prepared that without any of the GMP's consent, so GMP developers' consent, so we can fine-tune those names, but that's how these are grouped. Okay, in addition to those that are really developed within the working groups, we're going to consider also the Shajouei and Pezeshk. As far as I know, it's only it's not been published in a journal yet, but it's in the works. And we'll also consider the EPRI 2004-2006 review project models. So there's 10 individual models and 4.5 clusters, or 4 clusters with 2 different alternatives here. These are more known. We understand them better. Bob Young gave a really good presentation in July, so you can refer to that. So we're not going to re-present those. We're really going to focus on the new ones, but these are considered also in the evaluation. For the sigma candidate models, there's an ergodic sigma, so multiple models are going to be briefly presented by Linda and considered for our evaluation. The EPRI 2003, Atkinson and Adams 2013, Atkinson and Board 2006, and Toro et al. 97. The tau and phi additional will be from EPRI. And multiple phi SS studies, a lot of them from SSHAC projects conducted in the past. So Linda will expand a little bit on that on Thursday. So agenda overview is pretty simple. We have a short block of database and input updates this morning. Okay, so those are things that are used by the modelers. Then in the afternoon, we start with the proponent presentation, so Median Candidate GMPES. We continue tomorrow again with the Median Candidate GMPEs. And in the afternoon tomorrow, I forgot to say, we're comparing those GMPs and looking at them in the Salmon's map space. Be prepared. And after that, we're going to go over the standard deviation candidate GMPEs. So that's a more packaged task that Linda will present. Okay. So that's it for that. And we're running late, so I'm going to go quickly. My next presentation is really to just give you an update on what has changed in the database recently. So the NGE's Flatfile has been released within the project, so the GMPE developers, PPRP, and all those involved in the project. Still work in progress, as the database always is, but it's at a good usable state as it is. So the latest release was in September officially, and every time we release these, content may shift a little bit like in the airplane. So make sure if you have automatic readers that you allow for those changes in columns and text and check that. So this is just documented the recent changes or addition to the Flatfile, and I want to acknowledge there's tons of people work on it, but a lot of people really worked hard, including Tadahiro Kishida and Tim Manchetta, as well as other ones as well. So I'm just presenting here, just a messenger. So summary of changes is that we added the new USGS potentially induced event flag. So that's provided by Justin Rubinstein and Chuck Mueller. So we call them those PI, potentially induced events. New quality flag based on ground motion residuals developed by Tim Manchetta, similar to what he's done for West 2 project. The new set of quality flags based on record processing that came from the collective work of Chris Kramer, Tadahiro Kishida, and Olga Kenidou. I've revised the PAT regions. I'll show you that, and additional revised DS30 assignments for Canadian stations. So John Adams took the lead in further reviewing what we had done and communicating with the Geotech Working Group, and Grace Parker implemented those changes. So potentially induced event flag, it's a progress in discriminating induced or triggered events from tectonic ones, so that's mostly from deep well injections. That kind of work and discriminating is going to take a long time, way before NGEast, continue well after NGEast is completed. But in the meantime, the USGS, as part of the National Seismic Hazard Mapping Program, developed a list of potentially induced events. So it was shared with us. These events may not have been induced. We don't know for sure, but they're flagged because of the timing related to injection data and sequencing and all that. So if it's flagged as one, that's a potentially induced event. Then you'll hear this pie coming, pie events from Linda and Justin on Thursday. Okay, and then the quality flag based on ground motion residuals. This is really just a flag to sort out outliers that we didn't catch in processing. So Tim and Cheta led this effort, and they just used the Atkinson and Bohr 06 prime, so the 2011 version, to discriminate using different ground motion intensity measures, and the lines are plus and minus 4 sigma, so it's really large, but anything that fell off of that has been flagged as outside, potentially outlier. Of course, here you see we have some data that attenuates differently. Some of it's from the Gulf Coast, so that's why we allowed this wider range, and the GMPE is for the eastern U.S., so not Gulf Coast. So quality flags based on data issues, so that was mostly documented during processing. So we have a flag of 0 if everything's okay, or if we didn't notice anything weird or problematic. 1, if there are data issues that may impact the products, such as time series, TSA, SAS. So it could be, a short noise window, things like that, but it's probably fine. And then a flag 2 for data issues known to impact the products, like, for example, that we missed the first P or S arrival, things like that, but we left it in database for other reasons. So there's a lot of additional flags that define exactly what is the problem with those time series, so you can use your own judgment in selecting the data or using it or not. Then another thing that was improved is the regionalization is done on a record-per-record basis. So as many of you know, the CENA was divided in 4 distinct regions by the work of Walter, Mooney, and Chapman. This has been published in a peer report. And three flags are provided for those different regions. So there's an event region flag, so where the epicenter is. I'll show that in a map with a red star. The station region flag, so where the station is. And then what I call, it's a PAT flag, but it's event/region flag. It's a region of the full PAT from the event to the station is included in. Okay? This is recommended for using in regional studies. So previous Flatfile, I just subdivided the regions. We don't need to know what was done before. Let's focus on what's done now. So the first region is the Gulf Coast. Sorry, I'm just going to move that out of the way. So the Gulf Coast shown here, so events in red and stations in blue, and those are the black lines are the paths contained in the region. This is the Central North America, the largest region. Appalachian, region 3, and finally the Atlantic coastal plain. Then region 5 is as it was before, so that is allowing path crossings that were not contained in the pure regions before. So anything that crosses 2, 3, and 4, and it can have multiple path crossings, okay? So if you want to do, if we do go ahead and follow the recommendation from the regionalization group, we would group all those paths here with those from region 2, 3, and 4, and treat this whole big region as a single region. So previously, these were pure paths within the region, okay? And this is now what's remaining that's crossing between regions, okay? We added a Region 6, so we didn't have that before. Region 6 allows us to cross from the Gulf Coast to any of the other regions or from any of the other regions to the Gulf Coast. So that's a crossing of what we consider are going to be distinctive attenuation regions there. And then everything else that we left in the database, because it's still part of that general area, is those different paths here, and they have a flag -999. So that's it. Those are the latest improvements in the NG database. Quick question. So I don't have the agenda. I think the next is John Stewart. Okay. So John, you're going to use my phone. Yes, I'm sorry. Yeah, speakerphone is worse. Let's try that. I have a headset. Let me go retrieve that. So let's try the sound here. Can you guys hear better now? Can someone pick a name? Let's put somebody. Okay, Sanaz, can you hear okay now? I don't see your slides, John. Is it better? I cannot hear her. I can't tell from here. Good? Okay. Well, just complain away if it doesn't work. Okay? See?
So I don't need to hold the phone?
No, let's try without holding the phone.
So if they complain, then we'll go.
Okay. So John is going to provide an update on the VS30 assignment. So there's a bit of a chicken and the egg here. We're going to talk about the model he's basing his results on only on Thursday. But we can still follow along with the basic principle of what he's doing. Thank you.
Thanks, Christine. So I should explain that I'm in the Geotechnical Working Group, which is chaired by SSHAC. So the work I'm talking about is done with that group. As Christine mentioned, one of the things we're doing this year in the Geotechnical Working Group is working towards the development of the site amplification model. That process has to be iterative with the development of a GMPE, and that's what Christine was talking about. So we are, Grace Parker is a student with me, and I and the other members of the Geotechnical Working Group are communicating regularly with the TI team in that process. So what I'd like to talk about are some issues related. We haven't gotten to the point of site amplification yet, really. It's mostly issues related to data and trying to improve the site data as we go through the regression. So these are my 5 topics. Some new information based on site visits that have changed VS30 values. Sorting out various geological sources that can be used, some of which were used, some of which have not been used, and finding the current values of VS30 in the site database. I'd then like to talk a little bit about the analysis of site terms. This is actually a residual. I'll explain what I mean by that. And we've gone through a process of identifying sites that we think may have been misclassified. In other words, they have potentially the wrong VS30 value in the site database now. And I'll explain how we did that and then next steps. As I go through this, I'm going to be making reference to different codes that are assigned to sites. So every site has a code 0 through 5. And basically, as you go higher in number, the level of precision associated with the VS30 is going down. So 0 means it's measured at the site. That's the ideal case. There aren't very many like that. It's a tiny fraction of the overall sites. I think less than 100 out of about 1,400 sites. Number one is not bad. That's where somebody has visited the site, they've confirmed a certain type of geology, and there's a measurement of VS on that same geology someplace else. And so then we import that value of VS to the site. So code 1. And then basically codes 2 through 5 are where we don't have a measurement. And there are various sorts of proxies that are used to estimate VS30. In the interest of time, I won't go through that. Really what's important for today is knowing what code 1 means. The new information, as Christine mentioned, is coming from John Adams in Canada. It affects 40 stations. My understanding is each of these sites has been visited by somebody, so they're all code 1 sites. You can see that there's been personal communications with various people, the Canadian Geological Survey and University of Quebec. That's what CGS is not California Geological Survey, Canadian Geological Survey. Is that the right acronym? GSC? Okay. Sorry, I'll fix that. And there's various information from the literature that John Adams has provided. These references are all at the end. So of the 40 stations where we received information, 11 of them we haven't actually changed the VS30. 6 already had the recommended VS30 values, and 5 actually had measurements on site, so we didn't need to use the code 1 estimate. We've changed the VS30 for 29 sites, 21 of which the original VS30 was based on a hybrid slope geology proxy, and 5 of which were weighted various proxies. 8 stations already had a code 1 assignment, and then after reviewing the previous code 1 assignment and the new one was adopted. Okay, geological sources. So this is very important for the vast majority of sites. This is what the VS30 is based on. So here's what's available to our knowledge. So there's so-called surface materials maps. I'll explain more what that means in a moment. There's Fulton in Canada, Fullerton in the U.S., and these are what were used by Albert Kotke et al., this is Geotechnical Working Group, to develop a geology-based proxy for the East. Then there's another set of maps, which I'm calling surface materials combined with sediment thickness. This is Soller and Rahis. And this was used by Thompson and Silva for a hybrid slope geology proxy, which is also in the site database. And then there's various local maps that you can look up, some of which are for, say, 1 to 24,000 scale geology maps. Those have not been used thus far. The Fullerton, I give some specifics here. I think the main points to make is it's very, very large area being mapped. Okay, so it's truly a regional map, 1 to 2 million scale. It applies east of the Rockies, basically. And it's compiled from various maps that the USGS has put together. The references are there. There are many map units, something like 100, but they fall into 2 main categories, surface deposits and residual materials. Bedrock sites are not mapped with what you would normally associate with bedrock descriptions. You don't see granite, sandstone, limestone, things like that. They're actually mapped as saprolites, or basically in situ weathered rocks on this set of maps. So this is what the Fullerton map looks like. You can see that cutoff there just near the Rockies, east of the Rockies. Then the Fulton map for Canada covers the whole country of Canada, even larger scale, 1 to 5 million. Also surface materials, includes some offshore areas in addition to land. Broad categories of alluvium, lacustrine, marine, etc. They do have bedrock. And you can see some subdivision of units according to texture, thickness, and landform. So this is what the Fulton map looks like. And this information is already in the site database. The Soller and Rahis maps were originally 2004. They were updated in 2009. Again, very large scale, 1 to 5 million, covers the entire United States. These are actually the same as the Fullerton maps, in the central eastern U.S. They basically used the Fullerton map, but then just condensed the number of categories that were used. One difference, though, is that they've described bedrock differently. And so the units are described based on the composition of the rock underneath. So an example is a sedimentary limestone unit is described as residual materials developed in limestone and other carbonate rocks. So rocky materials appear in a different way than they did in Fullerton. An important distinction between this map and the Fullerton is that there are thickness estimates provided, but it's not a map quantity. It's not like you can go and look up a thickness that's specific to that location for that unit. There are really just thicknesses assigned to each geologic map unit. These thicknesses are important because oftentimes the thicknesses are under 30 meters. And so you're talking about a layer of, say, soil that sits on something much firmer that should be impacting the VS30. So the solar maps cover the entire U.S. You can see the map here. And then I've had the student, Grace Parker, look up more local maps, which haven't been used yet, and I'll explain why we're considering these a little later on. But just to introduce the resources first, there's the Quaternary Geologic Atlas of the U.S. That's at a million scale, and bedrock is actually mapped as bedrock. So it's easier, it's more familiar terms for us, maybe easier to interpret. And there are state geological maps which can be accessed through a USGS National Geologic map database. And I have the link there. These are at much more local scales, including 1 to 24,000. So just to give you an example of one site, this is New Hope, South Carolina. Right now, this site has a VS30 of 290 from Kotke et al. It's a Lacustrine Marine and Marsh group from the Kotke study, from the working group. If you go to the Fullerton map, this is where it plots, the red dot there. You can get an idea. It's mapped as beach and nearshore deposits. This is the solar map. And the thing to notice is that the shape of the geologic feature is the same here and here. Okay, that's because they're coming, the solar is derived from the Fullerton, so that's not a surprise. Apologize for the poor resolution of this, but this is the 1 to 24,000 scale map for that region. So this is showing a much smaller area in this image. The mapping is similar, but a little bit different in this case. So the reason why we're going through this geology, and I went through this here today, will become apparent later. These are basically resources that we can use to help resolve what might be the condition at sites where there seem to be problems. And so I'll circle back to that by the end. Okay, so now switching from maps to analysis of site terms. And I was actually hoping that the GMPEs would be presented before, but I'll try to explain what I mean here. Hopefully most of you are familiar with these terms. So to explain this, we have to speak about residuals. So residual is the difference between data and the median from the model. So the data is the LNY term, and the model is this term here. This is basically the GMPE. Okay? And then those residuals are partitions. We'll be hearing a lot about this, I think, maybe tomorrow, where we can separate out the event term. So that's the average bias, high or low, that an earthquake has relative to the median model. A site term. Okay, so an event term, a site term, and then the residual that's left over. This is just an overall bias that a particular GMPE might have. So the residual expression can be rewritten by just putting the data on the left, which is then the sum of the residual and the median model. And we can think of the site components. The site component of the residual is the site term. And the site component of the median model is the site term in the GMPE, which I'm calling F sub S. There are ultimately going to be different factors beyond just VS30 scaling. But for now, just focusing on that, that will look something like this. basically a regression coefficient C times the log of the VS30 divided by a reference velocity, which might be 760, for example. So the point that I want to make with this is that the sum of this eta sub S term and the sort of ergodic site term, the F sub S, that is the observed site response for a particular site L. L is the index I'm using for site here. And if one of these is off, it will directly affect the other. So the data is controlling the sum of those two. And so if, for example, we're assigning the wrong VS30 to a site for whatever reason, it will directly translate into this so that the sum remains the same. So just to sort of reinforce that point, this is the trend of the slope term that Justin Hollenbach and other members of the PI team have been getting. So this is that term that's multiplied by the log of the S30. That's what's on the y-axis, and then the x-axis is frequency. This is based on Fourier amplitudes. So the point I want to make here is that it's going from numbers, I apologize, it's hard to read this, but this is frequency of 1 going up to 100 in log scale. So it starts at about minus 0.5 and it trends towards 0 as you go to higher frequencies. Now, suppose just as a thought experiment that a site actually has a VS30 of 300 meters per second, but we mischaracterized its VS30. So what would happen is that the FS term would be wrong. And if we had mischaracterized this as, say, 150 in red, you would end up with an FS term that's too high up here, based on the C term. If you had mischaracterized it as 900, you would have an FS term that's too low. These lines are hard to see. I apologize for that. That would be down here. So that error in the FS term that's going into the regression would directly feed into the site term. So if the site doesn't have some strange response, non-ergodic response, this would cause this site term to trend in an equal and opposite way to what I just showed. Okay, so these site terms are computed and are being used to try to make judgments about possible misclassification of the S30. The peer model that Christine mentioned is being used for now, and it's based on Fourier amplitudes. We haven't run these regressions ourselves. We've gotten site terms from Justin. JH is Justin Hollenbach. And this is a continuous process. So they're always adjusting their model and sending us new terms, so it's pretty fluid. In order for a site to be used by us, it is having to have two conditions. So it needs to have a recording inside of 300 kilometers. And for now, we're not using recordings in the Gulf Coast region for reasons that I think will be explained later. It has to do with path, strange path effects, right? So there's 300, just to give some context, there's only 306 of these stations out of 1379. So this is a pretty modest subset of the overall database in terms of number of stations. In the interest of time, I'll skip that greater than 15 hertz part. So an example of this is what the site term looks like for one of the sites, station sequence number 71. The site term is on the y-axis, frequency is on the x-axis, and it's pretty flat at 0. So this is an example of a site that looks fine. Okay, there doesn't seem to be any problems here. The site on the right is one where the site terms are non-zero, and they're trending in a way that doesn't exactly mirror the C term, but certainly has a lot of common features in terms of its trend with frequency. Approaching 0, its frequency goes up, for example. So that's one we suspect there could be an issue. So how do we do that in a systematic way, going through all the sites? That's what this next section is about. So we're looking at the mean bias of the site terms and their slope in frequency space, in log frequency space. And we're assigning scores, in quotes, to each of these metrics This is completely a judgmental-based process. Someone else might do it differently, but we're just trying to put a number on the misfit so that we can organize the sites. So we average these scores, and then the higher the score is, the greater the potential for misclassification. So let me explain how this is done. We have a slope criteria. We're taking the site terms versus frequency, and we're basically fitting a line over one log cycle of frequency. So here would be 1. And then we move up one increment, and we do the same thing. So we have slopes measured many times over one log cycle of frequency. So there's many such slopes. Each log cycle has 100 points in it. Least squares regression gives a slope. We compute the maximum of these slopes for a site, and then we simply record that number. In this case, it's 0.68. This is an example of a site where there seems to be some problems. Then what we do is we basically rank these scores in terms of percentiles. So if it's a very high percentile, more than 90th, we just give it a score of 1. If it's less than 10th, we give it a score of 0, and we interpolate in between. This site that I'm showing here is a pretty good one in terms of slope. Its slope is 0.27, maximum slope 0.27. This ends up getting a very low score. So that's the slope. For bias, all we're doing is taking the average of the site term over the frequency range. This is an example of one that has a pretty large bias. Here's one that has a small bias, and we do a similar ranking based on percentiles of these. So we've gone through all this for the 306 sites. This is the histograms of the bias terms on the left and the slope terms on the right. You can kind of see the range there. It's hard to read, but this is going, and we're using absolute values, I should say, not keeping the sign. So this is 0 up to 1.4 for bias and 0 up to 1.4 for slope. And there's red lines here that are hard to see, which here and here for bias, here and here for slope, and those are the 10th and 90th percentiles. So this has all been computed and can be passed along to identify sites with misclassification potential. So in terms of next steps, what we can do right away is send that list to the PI team. This was just completed yesterday, so that's why we haven't sent it to you already. More importantly, and this will be iterative, I'm sure we'll have to update all this as the model changes. But what we're going to do is we're going to find sites that have high scores, that have this potential for misclassification, and then we're going to have to sort through what might be wrong with those, if anything. And so for sites that have high scores, this is where the geology comes in now. We'll look at the two geologic classifications we already have. Those are based on those surface maps, the solar maps and Fullerton or Fulton. We've looked through that not in a very rigorous way, but they generally seem to be pretty compatible, those two. So that may not be very useful. So what we think is going to be more useful is to look up the sites on these local geological maps, which is a long process, and also look them up on Google Earth and see if there might be something that tells us that the geology we've assigned to a site is not the right one. So this would lead to modified VS30s as applicable for those sites. This leaves the question of, what do we do for the other 1,000 sites? Right now we don't have an answer for that. This is only applying to sites where the data analysis flags it as potentially problematic. A related effort, which I haven't really talked about, is to re-examine the profile database. So this is a separate database of all VS profiles that the Geotechnical Working Group could find. This was work that was done some number of years ago. It was presented in a paper by Kotke. And there's some quality control steps that we need to go through to potentially remove profiles that we don't trust, that Joseph Harmon at Illinois has pointed out. But once we do that, we need to redo the process by which we assign weights to proxies, and this directly affects the VS30 assignments. Right now in the database report, it points out that the weights used to weights used for different proxies to assign VS30 are based on a very small data set, the less than 100 sites in the database. We can probably do at least an order of magnitude more data than that to constrain these weights. And so that is well worth doing, and we're going to be undertaking that task as well in the months to come. So that's it for me.
Okay, before we start on the questions, let me clarify a bit in terms of how this is norm. So
this is norm, yes.
You said mentioned there's a science program and then there's a SSHAC evaluation program. So when John talked about passing things, what this is part of the science program at PEER. He is not passing things back to the TI team to evaluate. Those are going back to the PEER science program to develop the candidate GMPE. The TI team's evaluation is going to be on the candidate models and moving forward. So we want to keep those two things separate. So just we'll change this to passing it back to PEER.
The PEER science team.
PEER science team and that whole evaluation. And it goes back to all the other developers that are working on it. So we'll make all that information available to them.
Right, because it goes in the database.
Correct. So this is all part. So any questions for John? Start with Gail. I can hardly see people out
here. Hi, John. I agree with that this is a good approach. So I'm not actually quibbling with the approach, but I'm wondering whether there's some inevitable circularity here that one introduces. In other words, that we end up classifying the sites so that they're what we want them to be. We don't really have any way of ground truthing if that's what they really are. And if there's some danger that we can end up fooling ourselves as to how well the approach works, because given ourselves the freedom to classify every site the way we like.
To some extent there is, although we're not actually using the data to change the VS30. So if what we were doing was taking a misfit and then adjusting the VS30 to remove that misfit, then that truly would be a circular. But we're not actually doing that. We're using the data analysis to flag sites that we should look more carefully at. In an ideal world with more budget and more time, we would look at every site in that way so that there would be no potential for circularity. And so this is really just a convenient way of keeping our workload manageable in terms of the number of sites we look at.
And just to follow up on that point, then in the ideal world, and what I'd really like to do is some sites that we flag this way, and we potentially misclassified, and then use your method to say what you think they are. Then it would be great to actually send somebody out there and determine whether you got it right or not.
That would be awesome, yeah.
I was wondering if you have tested this approach, the evaluation process for sites where we get certain known or measured or reliable.
Are you referring to a specific method, evolution approach? Mm-hmm. Yeah, okay. Yes, okay, I got you. Yes, and I didn't show that here, but if you, this is something that Justin Hollenbach has done. So if you look at the site terms that were computed for sites with measured VS30s, they average 0. Now there's some variations, of course, but so that suggests that the slope that he is getting, that C-term that he's getting out of his regressions, works fine for sites with measurements. Had it been different, there would have been a serious problem. So that was a fortunate outcome. Yes.
Ken.
Have you looked at H-speed ratios at some of these trouble sites to see if they're strong resonance? There's billions of studies in the literature that shows that sites that have strong resonance, it doesn't correlate well with the
We have not done that, but that's a good suggestion. We could.
Plus, it's easy to do. Yeah. You can do it without sending people out.
Yeah. Well, that gets back to the circularity argument that Gail brought up, right? You're using that.
Yeah, you can do it for every site. Right? I think they're going to find weird sites, BS30, not really characterizing the site well because the residents are being caused by BS30, but it's concept.
So we plan to look at things like that as part of the broader effort to develop site terms. We had not considered doing that in this particular effort of identifying potentially misclassified sites. But, ultimately it's possible that the site terms themselves could have components for residents that might capture something like that. So the HMRB might have a nice strong peak that could indicate residents. So something like that could end up going into the final model. Like I say, we just haven't used it at this scale for identifying potentially misclassified sites.
Jeff? No, you have to wait.
All right. Jeff Kimball from PPRP. Are you going to plot these to see if there's any geographic pattern to where there is the possible sites for this problem?
Yes, we will be doing that. And so that will connect with the geology. If a particular geologic condition is lighting up, then obviously that matters. Yeah. So, the process of identifying these high score sites literally finished yesterday. So we need to do some sort of interpretation and organization of that so that we can make those kinds of inferences. But that's a good suggestion.
A similar exercise is being done on the NGA West 2 data. So we have some of those as well that the sites show up as really a very strong pattern indicating we've got just the wrong site response. So if you get the site terms and they look like the inverse of the site response, then you probably have the site classified wrong. And so the same approach will work for that, and those will give us more sites where we actually may have a measured shear wave velocity to calibrate it in the same way. But this is going to be a big deal for us in terms of trying to figure out how do you go from the empirical data to 3,000 if you don't know where you're starting, what your empirical data is. That's really the key. If you want to add something, Christine? Okay, any other questions for John? No, okay, let's push on because we're about 2 minutes behind.
Thank you. So, Norm, your slides were ready in advance? Oh. How nice. Okay, there we go.
So no telephone,
We'll
right?
switch up the phone at the break.
Okay. All right. I will try to speak up so they can hear us on the phone. So I'm going to talk about the overall approach we're using to develop the logic tree. And so if you were here in July, this is a continuation of what we were talking about at that time. All right. So if you weren't here in July, this will go fast for you, but you should have, did we print out, Yusuf, Nico's handout? Okay, so over the internet, you should have got an email with Nico's explanation of what we're doing as well. So this is going to be a high-level summary of that. It's not. What do you want me to push? Okay, I pushed all 4 arrows and it hasn't moved, so.
You got the computer.
But the arrow doesn't work, is that right?
I don't know.
All right. What we're trying to do is get a set of ground motion models that are mutually exclusive and collectively exhaustive in their prediction of ground motion. Okay? So we're thinking about assigning weights to the ground motion that models that represent discretizing a continuous distribution of ground motion. So on the right, if I had given you a distribution and I would have said, all right, discretize it into 10 different models, you would simply sample it, and then we would give weights to those models based on the height of their bars. So straightforward, right? So the problem that we have is our candidate ground motion models, when we go to the literature or we're looking at what's been developed, give us only a small range of the full sample space of what could the ground motion models be. They also can be correlated, right? A lot of them are developed for the same data set, and so you can't consider these to be independent models. So they're not mutually exclusive. So mutually exclusive collectively exhaustive is what we're after. Okay, so when you see MECE, that's what we're talking about. So as a result, in the traditional approach of getting ground motion models, you may be assigning weights to them more based on relative merits of the model. You think this one is better, it has a better fundamental technical basis behind it, or it's based on larger data sets, or the functional form looks better to you, and so forth. So it's really a relative merit of the model and not discretizing a probability of that model representing a piece of the whole space of possible models. So how do we move to that? So how do we get mutually exclusive, collectively exhaustive ground motion prediction equation? The easiest way that can be done, and what's been done on other projects, is a scaled backbone approach. And we talked about this a bit back in July. So we select a single representative ground motion model in this approach, so one that you think behaves well. And then you're going to scale that one. That defines your backbone in terms of its magnitude and distance scaling and so forth. And now you're going to just scale that model up and down. So now in terms of probability, all that we're saying is there's a constant shift of that model. It could be higher or lower at all magnitudes and distances. And now I can define the distribution of that constant shift. What's the chance it's 50% higher? What's the chance it's 100% higher, and so forth. But it doesn't change for us the magnitude and distance scaling. So we can create mutually exclusive, collectively exhaustive ground motion models in terms of the amplitude at a given magnitude and distance, and it's well behaved and very simple to do, but we don't get the full range of possible ground motion models as they might change their scaling with distance or their scaling with magnitude, for example. So what we're trying to do instead, our Salmon's map approach, and this is the fundamental reason we're shifting to this approach, is that it captures alternative magnitude and distance scaling in addition to the constant terms. So now we're going to get mutually exclusive, collectively exhaustive set of ground motion models in the space of the Salmon's map. Okay, so our idea is, as we go forward, the Salmon's map, define all possible magnitude and distance and constant scaling in the ground motion models, and we're now simply discretizing that back to have a finite set of models to work with. Okay, that's basically what we're doing. So the scale backbone approach, I showed this back in July. This is what was done in BC Hydro. On the left is a set of ground motion models that were being considered, and on the right is a single representative model, and then it's scaled up and down. So we can capture the range that you get from these models over here, right? So at any point we can get the full range, but this has the same scaling at every distance, whereas over here you can see there's crossing. So by using the scale backbone approach, we lose information on how there might be differences in the scaling. The Salmon's map approach is going to preserve both the amplitude range as well as the differences in what the slopes are with magnitude and distance. Okay? Good so far? Yes? Okay. So our basic approach is what we're going to do. We are selecting a candidate set of GMPEs. So this is models that we think are applicable. At this point, we are not assigning weights to them. We're giving them a pass, no pass grade. So models that are, these are the ones that we want to be using. If a model has been updated with a new one and that's preferred, we drop the older one and we're just using those sets. There could be, though, limits on the application. So you may say this model only works up to this magnitude range or only works up to this distance range. And so we can do that, but we're not giving them any relative merit weights. It's you're in or you're out at this point, okay? Then what we want to do is we've got those sets, but those sets are not complete. They don't have all of the possible models. So we want to expand that space to start to create, interpolating and extrapolating those available models to build a whole continuous space of models that could be possible models. Okay? Then we're going to use this Salmon's map as a way of comparing the models and grouping models in terms of which ones are similar and which ones are different. Okay? Like in that continuous distribution of a normal distribution, if I want to say a value of 0.9 and a value of 0.91 are close enough, I'm going to group those together. I may be able to group models that have similar magnitude, distance, and constant scale together. Okay? So then we're going to take that map and we're going to discretize it into a manageable number of models to use on the logic tree. So I don't want to have 10,000 models that I'm running hazard with. I want to run 20 models or 30 models or something on that order. Okay? Then once we've discretized that, we need for each of the cells or discrete regions on that Salmon's map, we're going to select a representative ground motion model to use, and then we're going to assign the weights to those models, to that cell. And that's really where the main evaluation comes in. What is the weighting that is put on there? So initially, no weights are assigned. We use this to create a broad range of models. We're actually going to, in the extrapolation, we're going to push them to models that are probably should be rejected, which is fine. We build a broad space, and then we're going to chop out the ones that we don't consider to be credible, use the rest of them, and then assign the weights to those models. So I'll step through these one at a time. So the candidate selection, that's part of the evaluation phase for the TI team. Okay, so we'll go through what are the available models, and we'll be talking about what those models are today. Select ones that are considered applicable. That's the traditional way that you do it. The difference is we're not assigning weights to the models at this point. The second step is to expand the set of candidate models. So this is what was done on the SWIFT project. We'll do something similar, but there may be some other alternatives. But in that case, each candidate GMP was fit to a common functional form. We can find an equation that works pretty well for almost everyone's models. All of the GMPEs have the same basic kind of features to them. We do this on the footwall only, okay, and the reason for that is it's a much simpler set of models, and we'll deal with the hanging wall part later. We then evaluate the covariance of the coefficients. So I'm going to get the same coefficients for each model, and now I can compare how those coefficients change and how they're correlated. If you move up the constant, you need the distance scaling has to get higher, something like that to fit the same observation. At that point, again, equal weight is used for each of these candidate GMPEs, and we're going to then generate, in this case, a 2,000 new GMPEs sampling that covariance matrix. That means really generating new samples of coefficients that are consistent with the range of coefficients in our candidate GMPEs, and we go a little outside that range as opposed to inside the range. So this extrapolates and it interpolates. There will be some models that are produced that are not good, right? So we're going to restrict them to models that are, I put here, non-physical, but at least not behaving in ways that we want to constrain them. For example, I don't want the PSA going down with magnitude, even though that might come out of the pure statistical sampling. Okay, so then we're going to use the Salmon's map as a way to take these 2,000 models and do something with them. So what's shown here is Salmon's map, and the important points that you've all done your homework, I hope, and if not, you have tonight to read through Nico's write-up again. The thing that we care about is the distance apart in these models. So how far apart they are, their absolute location in space is not important, the relative distance away. In this case, the original GMPEs are shown here as red lines. We added additional epistemic uncertainty, or the blue points and the purple points. So that's the way we've done it in PEER, where we say the models are correlated. We need to bump up the epistemic uncertainty. The same thing is being done in the normal applications of these models. And then what's shown by these clouds of points are rupture distance-based models and joiner board-based distance models that extrapolate and interpolate between those. So we have now a big space here of models that are generated from the covariance matrix or the way the coefficients are related from one model to the next. Okay? So it samples that range. So then we need to, so I'm not going to run my hazard for thousands of models, so I need to discretize it. So now I'm just going to carve up this space. Okay? So behind this would have been our thousands of models, but we're going to sample this space and we make little regions here. And so each one of these is now discretizing a continuous distribution. It's no different than taking that normal distribution and saying I'm going to cut it down into 10 points. Then we're going to take this space and we're going to chop it down into, say, 20 or 30. How far out we go is part of the evaluation phase. There's going to be limits where we're generating models that really are so far off from the data that we don't want to bother creating them and then giving them zero weight, so we can do some of that initial pairing right away. Okay? So we then define these cells for our selected subregion. That's what's here. Don't worry about what's in the background. I'll get to that one in a second. So then, for each one of those, I'm going to have each one of these cells has a bunch of those models created. So I might have 100 models that fell into that one that I generated. I need to choose one representative one. So the way that we define representative is it should be representative in terms of its impact on hazard. Okay, so now I can turn that into a hazard curve and start to look at it that way. So we're going to take a simplified source model that is relevant for the east. So we'll have a background zone and then a large distance source in case showing up in there. We're going to then compute the hazard for each of the models. So this will be all 2,000 models, for example. We also then get within each cell what is the mean of the hazard from the 100 models, let's say, that fell into that cell. And then I'm going to select the GMPE whose hazard is closest to the mean. So in this way, I'm getting out of those 100 possible GMPEs the one who is best representing the average hazard, the mean hazard, for all of the ones that would fall in that cell. Okay? And that's all done on the footwall side. And that's because it's much simpler for us to develop a common model there. For the hanging wall, we're adding this at the end. So 5 hanging wall models have been developed separately. This is was done as part of the Swiss project. They're each with equal weight. And either we can add all 5 models and now multiply by 5 the number of ground motion models you need to run, or we'll randomly select one. And we're looking at using a random selection just so that we don't create another factor of 5 in terms of how many branches we have on our logic tree. These, though, then become the median models that are branches on the logic tree. Okay? So now the next thing we need to do is assign weights to those models. And how are we going to do that? How do you assign a weight to it? And this is really the main part of the evaluation phase that we have to go through. So one way to do it, and this is what's done on Swiss, would be looking at how the model compares to the relevant data. So we can compute the mean residual or mean event term from each of the models given the relevant data set. So you could take, in this case, the NGA East data set and a piece of it. Maybe it's only going to be magnitude 4s and larger or 5s and larger. And you could then compute for each of those ground motion models, each of the thousands of them, what is its mean? We get the residuals, so we break it into event terms, and so forth. We get the mean residual. So it's like the average bias. The model is 20% high or 30% low for this period. We can also get the likelihood. The likelihood being bringing along the standard deviation of the model. Is it producing the entire distribution properly as opposed to just the centered value? Right? And again, look at what Nico wrote in. It explains this in a little more detail. So we could be looking at NGA data sets for a given magnitude and distance range. We could also try to use some of the intensity data or the felt did you feel it reports converted to ground motion, given all of the uncertainty that comes along with it, it is still a large volume of data that we can use to potentially evaluate. And so from those, we can then say models that have closer to mean residual 0 should get higher weights than models that are out near the edges and so forth. The other approach is just what we call this as using the prior, or that is equal weighting, and that is when I sampled these models and generated them, let me just look at how many of the models fell into my cell. So if 10% of my 2,000 models fell into my cell, that cell gets 10% of the weight. If only 1% of the models fell into the cell, that cell gets 1% of the weight. That's appropriate if you believe the covariance matrix that you developed is the right way to go forward in terms of it's actually mean-centered and it's properly sampling things. Remember that covariance matrix used equal weighting. So this is back to saying all of the models that came through, if I gave them equal weighting, what would be the weights that I would give to each cell. So this is one way that these are done. So the contours that are shown in the background on the left are the mean event terms. It's hard to see here, but there's also contours on the likelihood. It's a little clearer on my screen here. But in these cases, as I go for models that I'm preferring are going to be near the mean 0 line, okay, and most of them will be that because they will derive from similar data sets. We can then say how far out are you going to go, 20, 30% in the mean, up and down, that could be a bias. These things are elongated in one direction because a mean residual, you can get the same mean residual even though you don't have the right slope on a curve, right? I could have fit the curve and get the mean, or I could have used the constant and still got the mean, but my variance is wrong. The likelihood calculations tighten that up and don't allow these contours to just go on infinite up way to high or low values, and so they limit the values in different directions here. So when we do all of this, the point is we can find a way to assign a weight to each one of these cells. Okay. The evaluation phase is what is the relevant data to be using for comparison, and should I be looking at the mean value, should I be looking at the distribution, and so forth. And then the other way, again, if I just gave equal weight to all of the models, we all pass to the equally weighted, what would we have come up with, and that can all be compared. So the summary of all of this is we are selecting candidate models. That's what we're talking about today. That's part of our evaluation phase. We're going to expand those space of models to create thousands of models that both interpolate and extrapolate. So we now think we have all of them there. Okay, in fact, more than you need. We're using the Salmon's maps, but you really need to understand what these things are because we're going to use that to define the continuous space. The reason for doing Salmon's maps is it now gives us a space that we can simply chop up. You can think of it now as it's a continuous grid space, and I'm just going to break it up into a finite number of grid points and move on. Okay? We're discretizing it into a manageable number, selecting a representative ground motion model for each of those, and assigning the weight. Simple, correct? Is that all clear what we're trying to do? Because what you're going to see as we're going forward today in terms of, you'll see some of the new models that are all developed put into the Salmon's map space. And the reason for that is this is how we're going to try to see where do these fit, are we really getting the whole range of models, and so forth. Okay. Question? Art?
USGS. I have a couple of comments, and I'm sure you thought about the backbone approach, for example. You showed that example from BC Hydro where GMPEs crossed, and you were using that as sort of make an envelope, I guess, around that. And one of my concerns is by doing that, you're sort of taking the worst case of all the models. Mm-hmm. Right? So you could be overestimating the hazard compared to if you actually did the hazard calculation for those individual GMPEs.
Correct.
It sort of ignores the correlation with those same GMPEs, you'd be getting a different set of hazard curves than you would by taking this envelope. I think you'd be overestimating the hazard.
And probably overestimating the range, at least, of what the hazard is first. Yeah. So that's why we're not doing it. Okay? So this is one way you get a continuous distribution. The reason we're going to the Salmon's maps is to avoid this issue, so that we will maintain the changing in the correlation of this slope.
Can you summarize his comments? People could not summarize.
Art was talking about the problems of shortcomings of using the scale backbone approach. This is scaling the model all the way up. And if you ran the hazard with this curve as opposed to the mean, you would get a higher hazard than if you actually took these models and had their proper correlation in there. So one model might be high at short distances, but it's low at long distances. It's not high everywhere. And so Art is suggesting or saying he doesn't think that the scale backbone approach is properly capturing the hazard.
The second point is on the Salmon maps, which congratulations for finding something that's really complicated. But the metric you're using is sort of a I guess, just reading it over from yesterday, the description is summing this metric of the differences in the ground motion over different magnitudes and distances. So some of that difference, that's not necessarily, I think you might have touched on this, but things that have large distances, separation in the salmon space may not have very big differences in hazards. If you look at the difference in hazards. And all this, I sort of worry that we're getting away from the science, and so it's physically plausible model. I'm sure you thought about this, but you're sort of taking a pragmatic approach to how to get this stuff. But it seems to me that you may be losing the physicality of the model by doing it.
So we create some models that are not physical, and then we're going to throw them out. So we don't just leave them in there. But the point is we're trying to say that the set of existing physically consistent models are not exhaustive, right? There are some we haven't built yet, right, or nobody has developed. And so we're trying to create those now so that I am fully capturing the uncertainty. And as these models are developed in the next 5 or 10 years, they won't suddenly fall outside of my range because I didn't have them. That's really what we're trying to do.
But again, some of it depends on the semantics that you're using, but sort of some overall the difference in the magnitude. You can say that the longer distances really don't matter.
Right. And so you could say one of the issues is in computing that distance metric, should we be putting weights on that but based on the deaggregation, for example? So the magnitudes and distances that are most important to the hazard, those are the ones we want to emphasize in terms of their differences in distance. So I think that's right. That's part of what we need to look at is really the distance metric that we're using for creating the Salmon map. Other questions? So Art did his homework. Thank you, Art. All right, I guess we're moving on.
Yes, we're moving on. Okay, so Nico will present some results. So tomorrow, right after lunch, when we're all fed and happy and relaxed, we're going to go over the salmon map and see where all the different models fall on there. Okay, so as you saw from my summary table, by the way, which I put online on the event website at the demand of John Stewart, so my intro slides are on the website, NG event, today's workshop. Okay. So there's a lot of models that rely on a point source stochastic approach. So what we've asked you to do is a summary of the point source stochastic approach. This is going to be useful every time things are referred to afterwards. And also it's a good lead into another thing parameter we will put in the database once it's fully computed is the kappa for the different sites. And so that's the lead-in for Bob Dara, who's going to do the presentation on SEPA. So we got the latest presentation from Gail up from the press this morning. Okay.
Thanks, Christine. Good morning, everyone. Yeah, Christine thought it might be useful if I just did a quick run-through of the basis of the stochastic point source simulation method that's being used a lot in this project for those that may not be that familiar. And apologies to the many of you in the room who know this stuff really well. You can just put your head down in your desk and have a nice little nap for the next 15 minutes. So I'll run through this really quickly. So I'm overviewing the point source stochastic method of simulating ground motion time histories, which can be used for a number of purposes: developing suites of time histories under a given seismological model for any magnitude, distance, site conditions. You can calculate response spectra, peak ground motion parameters from the time histories, or alternatively, and this causes a bit of confusion sometimes, you can get some of these peak ground motion parameters directly from random process theory without actually generating the time series, so that sometimes you'll hear people ask questions like, did you do this in the time domain or did you do it using random process theory? Two different flavors of the method. These methods are used an awful lot in ground motion prediction equation development in regions like NGAEs where there's limitations in the data. We have a lot of data now in the East, but it has some significant limitations in terms of the magnitude distance space that it covers. And for details of the method, I'll refer you to Dave Boer's many publications, and also thank Dave for a number of the slides, which he will recognize here because they're his slides. So basically, the stochastic simulation method, especially its point source approximation, is probably the very simplest possible way that one could do the general exercise of convolving source, path, and site effects, in which most of these effects are represented by simple empirical functions rather than physics-based models, as it were. And the aim here is essentially to just capture the main characteristics of the expected accelerogram in both the time domain as shown here. So in the time domain, the main characteristics would be things like the peak amplitude and the duration. Or in the frequency domain, then we would also be interested in characterizing the essential frequency content. What is the relative contribution of high frequencies to low frequencies, which are going to depend on both magnitude and distance. Just a note, why do we call it a stochastic simulation, and what's meant when you hear, say, a stochastic simulation versus a deterministic simulation? A deterministic simulation is generally one in which we begin with a description of the slip history on the fault and use theoretical wave propagation in a layered media and come up with a sort of wiggle by wiggle representation of the expected motion. And this method works generally best at low frequencies. At high frequencies, it's been found in many studies over the years that we can generate the expected motions well by taking randomized source properties that have some specified spectral content. And the aim here is to capture the main wave propagation effects by really simple functional forms. How much does the amplitude decay with distance, for example? And although these methods are very simple and make some approximations, which are actually pretty radical approximations, the method ends up working surprisingly well over a wider frequency range than some would think is fair even for such a simple model. So the basis of the stochastic model, and really the only seismological component of it, is the assumption that we have some target spectrum, like the one that's shown in the top graph, that describes the event, and that this target spectrum, this one little magical function, is essentially incorporating what we know about the source, path, and site effects. and we are taking the energy for that target spectrum, and we're assuming that it's basically distributed randomly over a duration whose length depends on magnitude and distance. And this is just an example from SMSIM, from Dave Boer's SMSIM program of two target spectra for magnitude 5 and a 7 and a simulated time series. So how is the time series actually simulated? And this is running through the time domain steps. And so first of all, the first thing we do is simply generate Gaussian noise. So what we're trying to do is just come up with a signal. It has random phase characteristics, a Gaussian distribution for the amplitude, and it has some duration, which is going to be a function of both source and path. So the bigger is the magnitude, the longer will be the source duration. The larger is the distance, the longer will be the path duration. And so that duration is going to be a function of magnitude and distance. And then in order to do this simulation on our computer, we're going to have some time steps. So that time step is a kind of a input parameter that is going to, with the duration combined, to map into what the array size is that we're going to be working with. So we start just by generating a Gaussian noise time series. Then we're going to window the noise, and the idea there is just to come up with a time series now that looks a little bit more like a seismogram. So if you just take a random noise sample and you multiply it by a window with a shape like the one shown there, you actually come up with something that looks a little bit like the S phase of a seismogram. And there are various windows that people have used, boxcars, cosine tapered boxcars. Popular one is the Ergodic heart window, which has got a nice exponential shape to it. Then if you transform that windowed noise into the frequency domain using a fast Fourier transform, you'll get a spectrum that looks something like this. And then we just need to shift that spectrum so that it has in essence, a unit spectral amplitude, so that it's not going to affect the total energy of the time series. So we can do that by just dividing the spectrum that we get by its RMS integral, and that will keep the energy content appropriate for the deterministic amplitude spectrum that we're now going to multiply this noise spectrum by. So now we've got a noise spectrum that basically has on average, a unity amplitude, and we're going to multiply it by a deterministic target amplitude spectrum. So now we've just created this spectrum shown here, and this target amplitude spectrum has, as I said, everything in it. It's got the convolution of the source, path, site response, and any instrument convolution that we want to put in there. In the frequency domain, all of these convolutions are simple multiplications, so it's very easy to do this. So now we have a normalized amplitude spectrum that it still has random phase characteristics. It's really just a noise spectrum that has the right frequency content in it. And then if we transform that back to the time domain using the inverse Fourier transform, now we have an acceleration time series that looks more or less like the S phase of a seismogram. So that gives us one empirical record. So if we sort of do one run, we get one random realization. And then this slide is just simply recapping the steps. Noise, window it, take its spectrum, normalize it, multiply it by the shape, then transform it back to the time domain. So that's really all it is. And then using this method, this is just an example of single realization in acceleration and velocity for a couple of different magnitudes and distances. A caution you should be aware of, the reason that you do many simulations is because if you do just one simulation, you might not closely match the target because there's random variability there. So any one simulation isn't necessarily going to closely match the target, but if you do tens or 100 simulations and you take their average, you will match the target. So that target amplitude spectrum, that's really the whole key to the success of the method. If you can get the target amplitude spectrum right, you will not be very far off in getting at least the response spectra of the ground motion. And so we really need to think about this spectrum as a function of magnitude, distance, and site condition. Right? This is the key element. So the components then of that spectrum are the earthquake source. So we need to say what is the spectrum as a function of magnitude and frequency. How is that spectrum modified as we travel? What are the propagation effects? How does that vary with distance and also with frequency? And how is that spectrum influenced by site response, which John just talked about? And then finally, sometimes people further convolve it if they want to get a Wood-Anderson response or the like. Now, most of these parameters in the stochastic method are determined empirically, and then that's just that. So the earthquake source term, there are various possible ways that we could model the earthquake source. It's going to have a constant term in it, and then essentially a shape term. And the most common assumption for the shape term is a simple omega squared balloon spectrum, but it doesn't have to be that. There are other possible models. You could have a double corner. You could have other features or whatever. This is all going to be the earthquake source spectral shape. Then the component for the propagation path is going to carry the functions that describe the geometric spreading and the inelastic attenuation. And so the geometric spreading is going to typically be R to some decay power, which it might be a simple linear function, it might be bilinear, it might be trilinear, and then the inelastic attenuation is generally the inverse of the quality factor or the Q function. The site response function is going to carry in it such factors as the kappa, which will be discussed in more detail in a few minutes, and then the instrument response. So then the parameters that we're going to need to specify this target spectrum. We're going to need a model of the earthquake source spectrum. As I said, most common is the Gruen model. We're going to need to describe how that spectrum is going to attenuate with distance. That's the path effect. And to do that, we're going to need to be able to describe the geometric spreading. How does that behave? And the inelastic attenuation. How does that behave? And as a note, while doing so, we might build in effective distance metrics so that we can better model near distance saturation effects. When we're modeling things as a point source, we're treating it, basically as all of the energy radiating from some particular point. And if we just do that without thought, we'll end up with very large ground motions near the source, whereas we know empirically we see these distance saturation effects. So a trick that has been very commonly employed that you'll hear more about today is defining an effective distance metric so that you can build in some of these empirically observed near-distance saturation effects. We'll need a model of the duration of motion so that we know what length the window is. And then we need some Prussell constants like the density, the velocity model, and so on, and near-surface attenuation, kappa, and any site response amplification function. The output of our simulation will be time series and response spectra if we use the time domain method. If we only use the random process theory method, we wouldn't get time series, but we could still compute response spectra. So those time series that we get will more or less look like what the S-wave package of a real record would look like, and it will have the right average response spectrum, but it might not have the same phasing or the same coherence structure as a real record that we would simulate if we used this deterministic methodology. So where did that come from? Okay. So I forgot. What is this slide doing? Okay. So this is just a one sort of by-the-side slide, and that is that I've just described to you the point source model. You will also hear something about the finite fault method, perhaps yes, perhaps no. In the stochastic simulation, you can also take the point source method and simply extend it to a finite fault geometrically by simulating a number of different point sources along a fault. That's all I wanted to mention about that. So the concluding remarks on that method then is it's a simple and effective simulation tool can model even larger, surprisingly well, even though we're assuming that all the energy is radiated from a point, if we use an effective distance metrics to define where that point is, and you'll hear more about that later. The reason it's so popular is because compared to more complicated methods, it requires very few input parameters. So you don't need to know as much about the processes of the source and the path as you might to effectively use a more complex method. The key to the method's performance is specifying the model components that include the source spectrum, how it decays with distance, the duration, and the site amplification. There's been a number of recent developments that you'll hear more about later today in improving the calibration of the method or the model to large empirical databases like both the NGA West 2 and the NGA East databases. And it's because the model is quite simple, it makes it possible to calibrate it to very large databases. It's easier to calibrate a simple model to a large database than to calibrate a complicated model to a large database. And that's, again, what's seen as a significant advantage. And there we go. Okay. So one of the additional things that I was asked to comment on is applying the simulations in NGA East, and in particular, the coupling of attenuation and source parameters. And this is input for work that I believe is feeding back into the PRT, correct? Yes, just for context. And so, as I noted, the key to the model is specifying the model spectrum correctly. And one of the really important things in this respect is that there's a coupling of the attenuation and the source model. Essentially, you can predict the same ground motion if you start with a strong source and attenuate it steeply as you could if you start with a weak source and attenuate it slowly. But you can't sort of pick these things independently. You can't say we've got a range of attenuation models and a range of source, and we're gonna combine them all just by all possible combinations. You have to consider jointly the attenuation and the source. So in order for the team to be able to do that, an exercise that was done was to select a range of representative Eastern attenuation models, more or less that span the center, the body, and the range of general attenuation models that are used. And then the team will be able, for each attenuation model, to find corresponding source parameters that would be consistent with that attenuation model. And so the selection of those attenuation models was work that was done largely by Justin Hollenbach, and he did an exhaustive literature search and compiled about 40 different attenuation models that have been proposed for the East in the literature over the last 20 years or so that cover that the distance range out to 500 kilometers. When he then looked at those 40, it actually kind of boiled down to about 20 that could be used to cover the whole distance range. Some of them only covered little pieces of it. And those models included a variety of functional form shapes: a simple linear decay overall distance, a bilinear, that's like a huge bilinear, so you've got one rate to say 50 kilometers and then another rate beyond, and trilinear shapes. The models are those that include both the geometric spreading and an anelastic attenuation component, and there's a whole different range of rates in different distance ranges that are included overall in that set of models. Some of them use 1 over R at close distances. Some of the more recent models use R to the minus 1.3 at close distance. And so what was done was to look at the plots of the attenuation shape, and in particular look at what the amount of amplitude decay in different distance ranges implied by the models was, in order to examine them and pick more or less judgmentally a suite of 6 representative models that span the range of attenuation. And so this is a plot of the 20 model shapes that Justin had. The amplitudes here are not important at all because, as I mentioned, these are all going to be used to determine sources that are consistent with the model. So it's only the shape that matters. The amplitude can be scaled up and down. It's essentially the shape that matters here. So here are the 20 different models. And then looking at those models, I characterized them so that I could look at them a little bit more easily by looking at the amount of attenuation or the log units of decay in 3 different distance ranges that are kind of critical in where the models vary. One of the distance ranges is the 10 to 50 kilometer distance range, and the next is 50 to 150, and finally 150 to 500 kilometers. And so what this plot is showing here is on the y-axis, you're seeing the number of log 10 amplitude units of decay for different models that are just numbered 1, 2, 3, 4, 5, through to 20. There's no particular meaning to the number. This is in the 3 different distance ranges. So the red is how much does Model 1 decay from 10 to 50 kilometers. The blue tells you how much does Model 1 decay, 1, 2, 3, etc., from 50 to 150, and then the green is how much does the model decay from 150 to 500. And then if you take the sum of all of those 3, you get the brown on top, which is the total amplitude decay of that particular model from 10 kilometers out to 500. The brown line that goes across is the average of the decay over all of the 20 models, and then the dotted lines just show its standard deviation. So an inspection was made over half a dozen frequencies, going from a half hertz up to 20 hertz, to look at how each of these models decay, and pick models that would kind of span the range in having types of behavior, linear, bilinear, and trilinear, and also span the range in terms of having relatively more or less attenuation. As I mentioned, this is just basically a judgment parameter to come up with 6 sample attenuations. And then this final slide just shows the 6 that were selected as covering the range, and they are the 6 models that are shown by the symbols, and then in the background is the full collection of 20. And again, it's really only the shape of the models that matter, not the actual absolute level at which they're plotted on this curve up or down. And so those models include a bilinear model, a 1 over R model, sort of at all distance with a constant Q, include trilinear models, and there's a range of attenuations in the first 50 kilometers from R to the minus 1 to R to the minus 1.3. By the time you get out to beyond 150 kilometers, pretty well all of the attenuation models in the East are using the common assumption of the R to the minus a half spreading, unless you've taken a linear 1 over R over all distances. And then the rest of the attenuation is taken up in the Q model. So that's just an overview. Questions? Just wanted to back there. The noise as the input in the model. So we need to characterize that noise thermal frequency or the
Yeah, her question is, is there any phasing or differentiation of frequency content and so on in the noise? And in the stochastic point source method, no, it's just a Gaussian noise. Is it which specific?
When you use the window, you apply the window to the
Yeah.
that window, how do you define it? Is it a targeting specific?
Yes, the window, the length of the window, the duration of the window depends on magnitude and distance. So there'll be a source component to the duration of the window, and there will be a path component to the duration of the window. So the duration of the window is a model parameter. One could also choose different shapes for the window.
Okay, I'm just going to remind everybody, we have few observer questions and comments on the end of the day. And if you have a question, you can ask me in the break. But we want to keep this focused on the CI team asking the questions mostly. And I'm sorry, I'm pointing to you. I didn't mean to fill the spot, but we're going to try to keep it focused on the CIP. There's a specific question on the most critical part of GM presentation is really the selection of the 6 models. Okay, everybody's happy? Let's
one
take
question
a quick
at the back.
Okay, and then we'll take a quick break.
I have a question about R-1.3 attenuation in the near field. If you can remind short, what's the basis for this? Because as far as I know, there are not many data points in this data.
There's 2 bases for R to the minus 1.3. One of them is empirical. If you look at empirical data in both the East and the West, they support an attenuation in the near distance range that's steeper than 1 over R. The other basis is theoretical. If you look at recent wave propagation studies in the literature by Chapman and others, for example, and in fact going all the way back to Somerville in the late 80s, 90s, you'll see that for a layered Earth, you would in fact expect spreading that is faster than 1 over R.
Okay, so we're going to go over a quick break and try to fix this phone issue. And, okay, it's 15 minutes, so let's start at 10:50. So I cannot hang up, otherwise we're going to lose the action. And I'll get the... Okay. Let me try to fix the phone issue. This and move, and you can play with it now.
Okay.
Okay, when Sahar No, that's good. I am. Let me try again.
You didn't give me that option.
Okay, so let me try again. *8.
test, 1, 2, check. Talking, saying things. The mic PA is out, but 1, 2. I'm gonna keep on telling stories and rambling, and there's no sound. But that's okay. The sound will come up, and we'll do test. 1, 2, 1, 2, test. This is good. This is ready. Everybody's happy. We're having a great meeting. It's fun. Yes, I'm trying to. Yes, they're testing. Without. Are you sharing now? No. Okay, that's okay. Go back to the. Okay. 1, 2, check, test. I'm speaking normal level. Speaking normal level. There's no sound. Trying 1, 2, check. 1, 2. If you hear, can you go and yes. So you have the phone number? Yeah, well, it's on the screen. CHC. 1, 2, check. I'm talking. There's nothing. There's no sound. Okay, cool. Yeah, because there's no sound right now.
I know.
Okay. Okay.
So test, check. Hello. Is this going to the phone? This is just a test to see if we're going to the phone. There's very little signal here that I hear actually coming into the mic at all. Are you going to the phone? Are you getting this into the phone line? This is a test. Check. Are you sending this to the phone? We're just going to keep talking until you find out if this is in the phone. Are you getting to
line on the hybrid box?
You can hear it? I'm sorry. Yes. So we need to now get it out of the hybrid box into the telephone line. So it's good that we're going to the box, but now how is it? So it's got to go out to the call. So why isn't it going out to the call? So check. Keep going. Keep working on it till you get it out to the conference call. I'm not hearing it on the conference call yet. Check. All right, now I hear it on the phone. Okay, that's good, but it's echoing. So why is it echoing? Check. All right, it seems to be working. But I hear an echo. Turn channel 6 down for a second, to output 6, and see if we still get it in the phone. It'll be gone, right, when you turn channel 6 down? Okay, so turn it back up. And it is up. But I'm not hearing it on my phone anymore. Oh, yes, I am. It's just very low. Okay. Is there anybody else on the conference able to hear? How will we? Yes. Okay, so we're good to go? Thank you. Sorry about the problem.
1 minute. Okay, everyone, we're going to start again. Please grab your coffee and come back to your chairs. Thank you. Okay, we're going to start. Group, we're going to have time to discuss more at lunch. Please take your seats. I'm going to start giving names. Gabriel Toro. You see, that works. That works. That's a dangerous one. Okay, so who else is disrupting? Youssef Bozorgnia. We need to start again. Dave Bohr is disrupting the meeting. Who else? John Ake is trying his best. Okay. Okay, everyone, we're starting. Can we have a bit more sound in the PA so I scare everybody, please? I get them into fear. Okay, good. To behave in fear. Who else is disrupting there? Bob Young? Chris Kramer? John Adams? I'm going to keep naming everybody.
I'll arrange with her to put it on a Dropbox and share the link. Okay. But you know you can log in live, right? The colors are better. Yeah. Okay, that's why I said that. But I will. Okay, so we're going to start again. So we're still in the database parameter addition, but we're converging also to model development here with this presentation from Bob Dara. It's basically they're using the models that Gail has summarized, the 6 models, doing an inversion, getting parameters such as kappa. He's going to explain everything. I don't want to do that for him, but and then this is one way that they're going to develop their own GMP as well. But the output coming from this work will also be shared with the rest of the project as part of the another release of the Flatfile. Okay, so Bob Dara.
Thanks, Christine. I'd also like to thank Gail for giving a very good introduction to some of the topics I'll be talking about today. And to paraphrase Christine from this morning, we'll be talking about kappa from broadband inversion. And our results are preliminary, but this is really, really fresh results. Okay. This is an outline of what I'll be talking about. I'm going to quickly define kappa, go over some of the broadband Fourier amplitude spectra inversion method. We're going to look at Central Eastern North America preliminary profiles that we've tied to 5 NEHRP categories. We're going to produce elastic amplification factors for each of the NEHRP categories. And then we're going to look at Region 1 and Region 2 from the division in the east. Region 1 is the Gulf Coast. Region 2 is the biggest CENA region. We're going to look at some data and initial data selection based on NEHRP factors, distance, and bandwidth. We're going to be using the 6 sets of attenuation and geometric spreading that Gail discussed, and we're going to be coming up with preliminary kappa knot estimates for 5 NEHRP categories in 2 regions. Okay, kappa, as everybody knows, models an observation by Anderson and Huff of energy dissipation in the top part of the crust. It's very critical for characterizing ground motions for engineering design, especially at frequencies above about 5 hertz. Okay, the inversion method was first done by Walt and others in an EPRI report back in '93, and it can be used to estimate kappa, in which use the point source method and the path and site parameters in a nonlinear least squares method to the Fourier amplitude spectra. We do the inversions on the log of the vector average of the 2 horizontal components. And one of the critical steps is looking at the bandwidth, and this will become particularly important in the east and is somewhat limiting with the transportable array data. So we look at if it's available, the pre-event noise, and the windowed SLG Fourier amplitude spectra. We also look at where the low-cut or anti-alias filters are in the data processing. Okay, this is an important point. The method gives kappa knot relative to a Brun source spectra and the assumed path attenuation and our calculated near source amplification for each of the NEHRP categories. One of the features or advantages of the method is we can treat multiple earthquakes and sites simultaneously, and that's what we're going to do. Again, I'm somewhat repeating myself. Flexibility to distinguish between sites for which kappa knot is determined and stations for which recordings are available. So we're going to have, for example, 8 earthquakes at a recorded 50 sites, and about 30 of the sites will be in common, shared between different earthquakes. Okay. These are the 5 inversion parameters that we can invert for: kappa, Q naught, eta, moment magnitude, and corner frequency. We're not going to invert for Q naught or eta. We're going to use the 6 Q naught eta pairs with geometric spreading that Gail has shown earlier this morning. We choose the final set of parameters by looking at the model fit to the Fourier amplitude spectra. We look at the mean, median ratio, and the parameter covariance matrix. Okay. So what do we need to run the model? So we need some preliminary crustal profile to get amplification factors, and these are elastic. And then we're going to use, which we haven't done yet, we're going to use the mean residuals in each NEHRP category to go back and correct these amplification factors. So currently, the amplification factors are preliminary. There's our first pass. We're going to use the specified combinations from Gale of crustal attenuation and geometric spreading, and we were using region-dependent ones in this study. And so kappa and the stress drop or stress parameter are relative to these input parameters. Okay. Here are our 5 preliminary profiles. We have 2 NEHRP A. Currently we're only using the roughly 2,000 meter per second VS30. NEHRP B at around 1170, C 560, D 270, and NEHRP E of 180 meters per second VS30. We've come up with profiles. The profiles are mainly driven by profile database from data in the West. You can see the E profile is the softest. It's furthest to your left, and these are going down to 500 feet or about 150 meters. Okay, this I mentioned before, we're going to get elastic amplification factors, and here they are. E is the highest. It goes at PGA or 100 hertz above a factor of 5. Then you can see the factor for D is here, C, B, and A at roughly 2,000 meters per second. This is A at 3,000 meters per second, and there's a slight amplification over unity because we're also including there the amplification from the source depth, which for most of these we're assuming is about 3.5 kilometers per second up to, in this case, 3 kilometers per second. So these are the linear elastic amplification factors that we include in the analysis. Okay. This is a slide I stole from Christine. We're going to first look at the Gulf Coast, and that's a small region to the south. These are all the sites, paths, and earthquakes that are only in Region 1 or the Gulf Coast. And here are 2 previous Gulf Coast models that were used. These were not in Gale's talk. So the first one is from EPRI 93, and it was used in the Silva-Dara, Greger and Dara model. It's going to be talked about later this afternoon. It has a simple functional form, and a Q is 300 to the 0.3. Second model we're going to compare to is a trilinear model from Chapman for the Gulf Coast, and he has a Q of 365 to the F of 0.62. These are previous models. These have not been vetted yet by the program, but we had to use something for the Gulf Coast. It's thought to be more appropriate to use these than the other 6, which are more developed for CENA. Okay. This is basically the whole Region 1 Gulf Coast data set. We have earthquake ID, and there are 8 earthquakes from 193 recordings. We're going to select from this set what we're going to look at. So I can tell you already, if there's only one event, we're going to not select those. The next biggest selection is on distance, and that affects the Comal, Texas earthquake the most. Most of those are TA array station sites at distances greater than our selection, and that one will drop from 121 sites down to 18. And also, that earthquake in Texas is a possibly induced earthquake, which is the PI acronym at the end. So here's our data selection for the Gulf Coast. We're taking everything within about 250 kilometers. Like I discussed, you need more than one site per earthquake. In the Gulf Coast, we're including TA recordings, so if you have more than 40 samples per second, we're taking it. We're including all data quality flags. We've looked at them a little bit, and we have one PI event. And the last one is if there's multiple recorders at the same site for the same earthquake, we've only selected one for this study, not to double count recorders at the same, similar recordings of the same earthquake. Okay, this is after reduction, and you'll notice that for we dropped the first two earthquakes. Shady Grove got reduced by 2, Minston, Tennessee by 1 station, Marston and Whitting, Missouri stayed the same, and the big drop was in Texas, went from 121 down to 18 stations. So now we're down to 85 recordings from 6 earthquakes at 49 unique sites. This shows you that some of the distance range of, we have both NEHRP categories on the left. There are no NEHRP A categories. There are only 3 NEHRP B and only 1 NEHRP E. So in this region, we're going to only really be able to determine C and D. The distance range, we're particularly interested in close-in distances, less than 50 kilometers. We have a pretty good distribution of earthquakes and distance ranges for these 6 earthquakes. We're going to see some results later, preliminary results from the Whiting, Missouri earthquake. It tends to have both well sampled in both C and D sites and tends to have some of the highest bandwidth. Bandwidth here is, if it's a TA station, you can tell that Comal, Texas, everything was recorded by TA. Whiting has actually some recordings with greater than 25 hertz Nyquist frequency, so we're going to look at that. For the C and D sites, at least preliminarily, we're finding that there's enough attenuation through kappa for C and D sites that even the limited bandwidth in TA allows us to resolve C and D kappas, at least in a preliminary way. When we go to the C, E, and A region, we do not use the TA array, at least in our preliminary data selection. Okay, so these are our preliminary results using the EPRI 1993 Q and G of R. The 2 ones that are really well determined are NEHRP C and NEHRP D. You can see we're getting about 0.24 seconds for kappa in C and about twice that in D. Amazingly, we get a little bit more, 50% more than D and E, but that's only based on sample size of 1. And here are the average VS30s from the sites we're using. And just to remind you, our amplification factors for B are based on a VS30 of 1170. For C, they're based on a VS30 of 560. For D, 270, and for E, 180. So that's using one model. Here is the second model, which is using the Chapman model. And he gets slightly higher values in here, and this is probably more instructive. This compares using the 2 G of R and QF models. We have fairly similar results for D, and that's, of course, the best determined. Close results for E, that's probably just fortuitous, and a factor 2 difference in our preliminary estimates for Site C for the Gulf Coast. This shows one interesting results. We're also inverting for stress drop or stress parameter. For all the non-pi earthquakes, we're getting large stress parameters. For the pi event, we've seen this in other inversions I'm not going to show today. We're getting very low estimates for the stress parameter for the induced earthquake in Texas. All right, here's an example. This is one of the best recorded earthquakes we have. Large bandwidth, lots of stations within 50 kilometers. And we're just going to show 9, results from 9. Okay, so each earthquake is in its own little square, and there are 3 curves in each square. That usually the curve that's the bottom is the dashed line. That's the initial model, and that goes goes in using the moment as reported in the flat file, and we start with initial kappa estimate of 0.02 seconds. And this is for 9 of the 17 D sites. The data is solid, and the Bruin model fit and the G of R and Q fit are the dashed dot lines. And what's important to see or look at is, let's look at this one. This one has nice bandwidth. Here's the initial starting model in dashed, and you can see that at high frequencies, both the data and the model are at a steeper slope, and we're getting a kappa higher, roughly 0.04 seconds, for this NEHRP category. You can see some of the data is limited in bandwidth. In the flat file, you can see some nice resonance peaks in some of the data set. But this is in general, a fairly good fit to broadband data. Okay. So now we're going to look up in the CENA. Since we're not going to, at least in this first pass, look at TA stations, all this data cluster out here goes away, and they would have been eliminated based on distance criteria, but basically they're eliminated on a bandwidth criteria. In this region, we're mainly looking at hard rock sites, NEHRP A and NEHRP B. And so we're going to end up, when you see the data selection, we're basically looking at Canadian stations, Canadian earthquakes, with one earthquake in Upper New York is what we're left with after our preliminary data selection. So this is what we did for Region 2. Restricted Haifa Central a little closer because there's just more data. We wanted to get something done for this presentation. And each earthquake has at least one NEHRP site A, and that's because we're emphasizing kappa naught at A and B sites. We've currently cut out all TA array recordings. We want broader bandwidth, especially at high frequency. We've checked some data quality flags, and there are 5 sites in there that fit TIMS plus or minus -4 sigma. Including or not including those doesn't change the preliminary results very much. We take pi events, but they all get excluded based on other criteria, mainly the DT. Okay. Now these are the 6 models that Gail discussed earlier. So we have Atkinson and Bohr 2014, Bohr, Campbell, and Atkinson, a trilinear model, another Bohr, Campbell, and Atkinson linear with constant Q, Bohr, Wright, and Seekins, early Joyner model, and what everybody else calls, I think, SO2SC for Silva 2002 single corner. Actually, we borrowed that from EPRI, so we're just using that as called EPRI 93. So if you see EPRI 93, it's the same as Silva 02 single corner model. And we also use the Silva 02 single corner model in the Gulf. The main difference there, these 2 terms were the same. The main difference was in the Q model between Central Eastern North America and the Gulf. Okay, so those are the 6 models. This is the data. There's just a lot more data, and it gives you the magnitude and the number of stations. I don't need to dwell on this, but you'll notice that most of the earthquakes are in Canada except for Sable Forks in New York. Here's more of the data. And this shows you what we have in our classes. There's 2 pages of this. But here we have a lot of NEHRP A sites and fairly good representation in close. And here's the total. So we're going to look at 28 earthquakes from almost 200 sites. 135 of them are NEHRP A, so we're really focused on the hard rock sites in CNA. We have 30 from B, and then it drops off quickly as we go out to C, D, and E NEHRP classes. Nearly 100 within 50 kilometers, and less as we go out to greater distances. Okay. So here are just a summary of how many sites we have in each. So for A we have 133 recordings from just roughly 26 unique sites. So on average, there's about 4 recordings per site. B, it's closer to 2 on average. C, it's almost 1. And D, there's a huge drop-off in D and E. Again, the average VS30 is 1931. We're using 2032 for our elastic amplification factors. Here for B, it's 1212. We're using 1170. And as we go down the list, our averages are fairly close for the amplification factors to our average VS30 from the Flatfile. Okay. This goes over the results, and I've grouped them in kind of firm rock, stiff and soft soil, and very soft soil to give you an idea. Going across the top are the 6 combined Q and geometric spreading models. You can see the difference. If you look at A sites, there are 5 that are around 0.08 seconds. The EPRI 93 model gives a larger value for kappa naught, and the main reason for that is if you look at the Q model for that, at a Q of about 20 hertz, which is kind of the midpoint of the data for estimating kappa, that Q model is twice as high as basically the Qs for the other models, except the constant Q model. So Q for this one is roughly 4,000. Some of these are basically in the order of 1,000 to 2850. And so if you have a larger Q, the data is going to, less attenuation, the data is going to force the larger kappa to fit the model. So that's what we're seeing. That's what we're seeing on this slide. And now we're going to look at the data. This is, again, one of the better recorded data, earthquakes. There are 8 sites in close. And we're going to look at the Atkinson-Bohr 2014 model for geometric attenuation in Q. Again, these plots are similar. This earthquake has pretty good bandwidth. You can see the starting model, and you can see in some of these that we're losing resolution at high frequencies, where it's difficult to resolve kappa at some of these sites. But this is, again, a fairly good preliminary fit to the data. And these are averages of preliminary kappa naught estimates. So we're getting about 8 milliseconds in region 2, and that's averaging, linear average over the 6 geometric spreading and Q models. For B, we're getting twice that. Again, just looking at the region 2 data. For the last 3, I switched to the region 1 data set because of how the data is distributed. And we're getting about 36 milliseconds for C, 51 for D, and 66 for E. But again, that's only based on one site. But 2 different models for geometric spreading and Q. So those are our preliminary estimates for kappa for the 5 NEHRP categories. There's a couple issues that we're going to look at just quickly. One is, as John had referred to earlier, there's still some uncertainty in VS assignments. One of the earthquakes that is posing a challenge to us is the 2 Val-de-Bois aftershocks. They have quite a bit of recordings in close at stiff sites, A and B sites. And Olga has graciously volunteered to help us hopefully resolve some of this issue. I'm going to show you the similar plot for the B sites. If you look at the data at several of these sites, it's almost linear at a mega squared model, and by the time the bandwidth stops, we see no rollover at high frequencies in these earthquakes. The corner frequency in the model wants to be pushed to very high frequencies because of this linear trend. We do see in the model fit that there is some rollover. That's because we're fitting all NEHRP B sites simultaneously. So this fit is controlled by other NEHRP B sites that have more rollover at high frequency. So this would be some candidate sites. Most of these are temporary sites that were put in, I believe, after the earthquake. Those are the ones with the serial numbers. Orleans, Innsrode, and Alfred have recorded, Alfred's recorded about 4 other earthquakes, Orleans, Innsrode about 8 or 9. The data, for the most part, shows similar trends, except perhaps for the main shock, where these are slightly different distances. So that's one of the things we want to look at to try and resolve what's happening in this earthquake and some of the other ones. So what we need to do in the future is we're going to add stations and earthquakes to try and improve our resolution of kappa and the stress parameter. We may divide Neherp A into 2 groups. There's kind of a bimodal distribution in Neherp A. There's a lot of sites with a VS30 at 2,000 meters per second, and then there's another group with VS30s clustering close to right around the boundary, 15 to 1,600. If we have adequate information, to do that. Then we're going to correct the elastic amplification factors with our revised mean residuals, and then redo the inversions. And here, just for completeness, are the references that we've been using. And thank you very much.
Is there any question for Bob? Bob.
So, Bob, this is Bob Youngs. You mentioned that you were getting lower stress parameters for the pi events.
Correct.
Do you have sufficient earthquakes in the area where the other non-pi events in the same areas where you have pi events?
No.
So we don't know whether that's a pi effect or a regional effect.
Correct. Yeah. And I don't think the data exists currently to resolve that.
This is Norman, but there's a depth difference as well, right? So the pi events are shallower. So all of that stuff, you don't know what the cause is.
This is Rob Graves. Just to comment on that, there has been some work Sue Huff has been doing that does support a more systematic behavior of low stress drop for the pi type events. So even though in this data set there's only the one, I think in a broader examination there is some evidence to support the lower stress drop.
I'll just pick up on that, Gil Atkinson. Yes, and Emma in his presentation will also show some more work of that type. I think that it is largely a focal depth effect, that the pi events do seem to have a lower stress drop because of their low focal depth.
This is Chris Kramer. Just a comment about Sue Huff based on intensity. Most of the pi events are in the Oklahoma, Arkansas area. I got one. And, okay, not being forceful enough. Well, anyway, they are near the boundary between mid-continental high Q and Gulf Coast low Q. And some of her interpretation does not account for those differences in Q. And the only pi event that she now analyzes that is not down there is in Ohio, and that shows much less of a difference in stress drop. This comment doesn't preclude the possibility of a difference in stress drop. They just have to be careful with Sue's published analysis.
Bob, this is Jack Boatwright. Can we get back to your methodology rather than the events you didn't analyze? It seems to me that your methodology depends upon the presumption that there is not a resonant structure in the spectra, that you don't have a resonant peak from in your data because you're not modeling any resonances directly.
Correct. We just smooth right through it.
The point I would make is that certainly in some of the B sites in Canada, and actually in one of the, I presume it's an A, LMQ sites, there are resonances. LMQ's got like a 10 hertz resonance you can't get away from. So how do you handle those sites? Do you exclude them? Do you even look for resonances? Do they all go into the hopper?
Currently, they all go into the hopper. And then when we look at plots like this, we can see stations have resonances. And if it's common between the sites over all the earthquakes, we may exclude it later or put it in a separate class, but we don't have the VS structure to pull out. We could come up with a resonance model and remove that, but that's beyond the scope of this exercise.
Yes, Gabe, can you, TI team, pass the mic? Where is it? Oh, we're supposed to keep one.
Oh. I'll let them go first.
Yeah, just one comment, echoing what Jack said. I think it's very important to keep in mind how that kappa is going to be used. So if it's going to be used in a forward sense with an amplification model, then that amplification model should be included in this analysis. If that kappa is going to be used as a shape parameter on the final spectrum, then this is okay. But it's always that issue of compatibility between the way you derive the parameters and the way you're going to use them in a forward sense.
This is our cycle.
Let me just clarify that. So the main purpose of them doing their inversions is that they're going to use those parameters back in their forward simulations. So it's self-consistent with what they're doing in that sense. The other methods would use the 3,000 meters per second, kappa is 0.006. So that's constrained. That's our hard rock. You want to?
So you will not use amps in that forward simulation, or will you have any crustal amplification? Or will they have any crustal amplification in that forward simulation?
Yeah, we're going to include whatever G of R and Q model and amps in the forward simulation.
And
so they're all coupled together.
Okay, but that's where the problem comes in. If you're using amps in the forward sense and you're not using them here, there is a little disconnect.
We're using amps here.
Oh, there is amps. Okay,
yeah.
but it's generic. Okay,
but
it's not site specific. Okay,
they're generic, but we're going to study the residuals and improve the amplification. So.
Oh, okay.
Here are the amps.
Oh, okay.
Those are the ones we're using now. We're going to look at the residuals once we, and then we're going to tweak the amps.
Okay, then you're consistent. At least may not be consistent site to site, but in general, overall, there's no gross inconsistency. Good.
So just to recap on this approach, they fix the Q geometrical spreading based on the models. They get the site amplifications from their generic profiles. Those are kind of input constraints on their inversion to obtain the other parameters. And in the forward sense, they use them self-consistently. Is that a nice? Okay.
That's correct.
Okay. So Art Frankel.
Okay. Well, I do agree with Jack's comment that you really need to look at resonances. And the best way to do this whole problem would be to invert for the site response at the same time as you're trying to get and then break down the kappa somehow. But my question to you, Bob, how much trade-off do you think there is between stress drop and kappa? You had some pretty high stress drops that you showed in the early part of your talk, and also pretty high kappas in that part of the talk. I would think, especially for the limited bandwidth you have, that there would be a lot of trade-offs between kappa and stress drop.
Yeah, and corner frequency. You can
well, that's what I'm talking. Corner frequency leading you to have trade-off with stress drop.
You can see that particularly in the one we're having problems with. these are giving very high stress drops, very high corner frequencies, order of, thousands of bars in the initial inversion. Part of it is looking at the solid lines. A lot of them are basically straight lines at about a mega squared. There's no out to, a lot of these go out to about 20 or 30 hertz. We don't see any effects of either Q because they're enclosed. These are all within about 50 kilometers, or kappa at, these are B sites. So we might expect to see, more of an effect of kappa. But all of our parameters are coupled together. And we look at the covariance matrix, to see the coupling.
And you showed one slide where I thought the kappa seemed to decrease with for site, class E sites. I thought.
Yes.
What was that all about?
There's only one. E is very poorly represented. So in this one for E, there's only 5 sites. So E is being driven by corner frequencies being fixed by the rest of the sites in that same earthquake. So we just included E for completeness, but in the whole NGA East data set, there's only about 7 or 8 E recordings. So only fortuitously the Gulf zone did it actually come out larger, but it's at one site. There's no statistical significance to that. It's just, but it looked nice, so I kept it.
Okay. No?
Thanks.
We're trying to deal with correlated sets of parameters, and so for kappa, do we need to keep that separate for each of the geometrical spreading and Q models? Because you had, in the end, given an average kappa.
Correct.
So are you recommending the use of the average kappa or the use of the model-specific kappas?
I would recommend using the model-specific kappa, but for some of these, for most of the ones here, the only model that's significantly different is the EPRI 93 model. They're all get basically, the same.
So we could group them into 2 parts, but that one's got to be done separately, right?
Right. Yeah.
Okay. Just a clarification again, and Emily will come to you in a second. The idea is to have suites of GMPs that are based on the skew and geometrical spreading. So there's going to be 6 GMPs that will come with their own correlated sets. So, you can keep them separate as part of the modeling in a forward sense, the same way. We don't need to group anything yet. Anyways. Anne-Marie.
Anne-Marie Balte. I'm not sure if I'm allowed to talk, so. On the slide we were looking at before, I think 25 or something, it seemed like the moments were way off. Is there something sorry, louder? Maybe 24. Yeah, it seems like the moments were way off on the initial estimate. Is there something that I'm not catching about the inversion, or the moments poorly constrained initially? Why don't those match?
The moment is, so in our inversion, the moment gets shifted around. The moment magnitude changes. So we try and fit the long period. So for this earthquake, it's a magnitude 3.4, and we only have a very small subset of the data. So we could be at azimuths and distances where, our data is just, in this case, higher at long periods than, the global. And moment magnitudes for 3.42 are difficult to obtain.
So is this just for this example earthquake at these distances, or is that a trend for a lot of these events? And should you redefine the moment then? I don't know, maybe Jack has something to say.
In the inversion, so we start off with the moment in the Flatfile. So in inversion, some moments go up, some moment magnitudes go down. There's trade-offs. We're just trying to fit the long period with a very simple Bruin model. And if you notice, most of these curves are only going out to 1 hertz, and moment is more longer period. So we're not really sampling out to 10 seconds in any of these.
Okay.
So Yeah, moment gets recalculated in the model.
I guess I was asking if the moment gets recalculated, should you update the moment in the flat file?
Well, it depends on the particular Q model and GFR model that we're using. So we can come up with 6. I can give you 6 different moments, but and it's only inverting a very small subset of the whole data. And for some of these small ones, I'm not sure. The moment is probably not a true moment magnitude in Flatfile. There aren't moments for 3.42s. So they're probably coming from a conversion from MB or from a local. But that's only my supposition.
There are some moment estimates for magnitudes down as small as 3 that have come from the literature that were used in the flat file. Some of them are converted from other scales, and some of them are actual moment estimates.
And can I find that out in the flat file? Is there a code?
You have to talk to the boss man.
We'll give you, so it's in the flat file, but we'll give you, we're going to post very soon publicly the actual event file that has more details on it, on where these moments came from. Exactly. That the Bob Youngs developed for us. Okay, we need to move on. Thank you very much, Bob. And Bob is going to come back and talk about the forward modeling this afternoon. So the first actual GMPE talk is coming now. So that's our first. We're switching gears until lunch tomorrow. We're going to talk now about GMPE proponent models, and we'll have Imra Yenye present right now.
Thank you, Kristen. Hello, everyone. My name is Imra Yenye. I'm attending from Western University. Today I'm going to briefly summarize our most recent research. The title of my presentation is Regionally Adjustable Generic GMPE based on equivalent point source simulations and application to Central and Eastern North America. This work was supervised by my supervisor, Dr. Gail Atkinson, and it is going to be submitted soon in BSSA. So as an introduction, the limited empirical data, limited ground motion data in Central and Eastern North America restricts the derivation of empirical prediction equations for wide magnitude and distance ranges. But there are alternative methods to develop GMPs in data poor regions. For example, you can use simulations to generate ground motions compatible with regional source and attenuation parameters for prediction purposes, or you can use hybrid empirical method by using a empirically well-constrained GMP developed in a data-rich host region and calibrate this host GMP to a target region using the adjustment factors obtained from simulations in the target and host regions. Another method is called reference empirical method. It is similar to the hybrid empirical method in concept, but the adjustment factors are obtained from the spectral ratios of ground motions observed in the target region to the predictions in the predictions from the host GMP. In this study, we take the advantage of key concepts in all these approaches to develop a robust simulation-based generic GMP that allows adjustment for use in any region by modifying a few model parameters. So in this respect, we first generate ground motion using equivalent point source method with parameters calibrated to observed data in California, and we decouple the effects of source and attenuation parameters on the response spectrum and peak motions by means of regression analysis. And using these decoupled effects, we parameterize the generic GMPE as a function of magnitude, distance, saturation term, stress parameter, geometrical spreading rate, and anostic attenuation coefficient. This parameterization actually provides a generic GMPE that can be adjusted for source and attenuation attributes in any region. And it also allows an effective and transparent control on the transferable factors between regions. In the generic GMPE, we have also an empirical calibration factor to account for the effects missing or different in simulations. This closes the gap between simulations and the observed data in the target region. So our generic GMPE has this simple functional form. From left to right, we have functions for source effect, geometrical spreading, anostic attenuation, and site effects, and a final parameter as a calibration factor. We determine the source effect and geometrical spreading functions from the simulations, and all other three parameters or functions are determined empirically. We adopt the site effects model proposed in BSSA 14 in our generic GMPE, and we provide predictions for PGA, PGV, and 5% damped pseudospectral acceleration up to 10 seconds. So the source effect is given by this function. The first term represents the magnitude effect if there were no saturation effect for a fixed stress parameter of 100 bars. We model the saturation effect by means of the geometrical spreading function. And the second term represents the stress adjustment needed when the stress parameter is different than 100 bars. We use a quadratic hinged functional form to define the magnitude effect. Here, E0, E1, E2, and E3, and also magnitude, hinge magnitude, MH, are the period-dependent model coefficients. And the stress adjustment factor is given by this equation here. So the stress parameter is an independent variable. It allows us to calculate the stress parameter from the PSA data in the target region. This E delta sigma term represents the rate of ground motion scaling with stress parameter. It is a function of magnitude and period. So the geometrical spreading function is given by this equation here. The first term is the geometrical attenuation of Fourier amplitudes, and the second term represents the change in apparent attenuation when you switch from Fourier spectrum to response spectrum. We model the geometrical spreading based on the equivalent point source approach as a function of effective distance given by this equation here. The derupt term is the rupture distance, closest rupture distance, and the H parameter here is the saturation term that controls the saturation of ground motions at close distances. We define the geometrical attenuation of Fourier amplitudes, the Z term, using this bilinear shape with a transition distance at 50 kilometers and attenuation rate of -1.3 at close distances and -0.5 at far distance. Recent empirical studies showed that these parameters and shape, the bilinear shape, can provide average ground motions, can provide successful predictions for average ground motions in many regions, including Western and Eastern North America. But if you want to use, although we fix the shape and the attenuation rate in the generic GMPE, this function here allows the users to modify the geometrical spreading of Fourier amplitudes for different shapes and attenuation rates if compelling evidence is found in the target region. So to consider the extension of saturation effects to further distances with magnitude, we define this H parameter as a function of magnitude. And this equation is determined based on the loose interpretation of recent empirical studies while avoiding the oversaturation of predicted amplitudes for large earthquakes. So the attenuation, the analytic attenuation is determined from the ground motions in the target region based on this functional form. Here, gamma term is the analytic attenuation coefficient. We define the site effects relative to the Nieherth BC site condition, considering the linear and nonlinear side effects as defined in BSSA 14. And after calibrating the generic GMP to target region, we determine the calibration factor needed based on the analysis of residuals. So we determine the model coefficients for magnitude effect, stress adjustment factor, and geometrical spreading function based on the equivalent point source simulations. We use the parameters calibrated to ground motions obtained in California, as suggested in one of our recent research, as discussed in Yenier and Atkinson 2014b. Briefly, we use a double corner source model from Boer et al. 2014 with a spectral SEC that's calibrated to observed motions in California. We use the same geometrical spreading and the close distance saturation as I discussed in earlier slides. We do not include any analytic attenuation in the simulations because this term is determined empirically. And we use the crosstal amplifications proposed by Atkinson and Boer 2006 for Nieherth BC site condition, assuming that the kappa factor is 0.025 seconds. The ground motion duration is given as the summation of source duration and path duration. The source duration is determined from the uniform weights of the uniformly average of the corner frequencies from source spectrum, and the path duration is determined or defined based on the recommendation from Boer and Thompson 2014. I should note that if there are any inconsistencies between simulations and the empirical data in the target region, this will be mapped into the calibration factor C. So we determine the model coefficients of magnitude effect and geometrical spreading from simulations generated between magnitude 3 and 8 up to distances 400 kilometers with a fixed stress parameter. We use the simulations at 1 kilometer to determine the model coefficients for magnitude effects. Because the simulations include both magnitude effect and saturation effects, we constrain the regressions with the saturation effects imposed by the imposed in the simulations by this equation here. This allows all unsaturated magnitude effects to the FM term. Then we play back the magnitude effects from all simulations at all magnitudes and distances and regress the resultant motions based on this equation, which is the geometrical spreading function. Again, we constrain the regressions with the model we assumed in simulations, and this allows the difference between decay rates of Fourier amplitude and response spectrum to the second term, which are defined by B3 and B4 coefficients. So this figure shows the simulations pseudospectral acceleration at 1 kilometer on the vertical axis and moment magnitudes on the horizontal axis for different periods in different panels. The circles represent the simulated amplitudes, and the solid line is the fitted model as given here. So our fitted model gives a good agreement with the simulations. As you can see, we have saturation effects by this term, and the saturation effects decrease with at longer periods. So this is an overall comparison of the simulations versus the fitted generic GMPE. We have pseudospectral acceleration on vertical axis and rupture distance on the horizontal axis. Each symbol represents different magnitude simulations, and lines again shows the generic GMPE we developed from the regressions. One thing I want to note here that, as you can see, the saturation effects increases to further distances, extends to further distances with increasing magnitude. And also, we have this magnitude-dependent attenuation rates, which are like observed in the empirical data. So this suggests that our generic GMPE represents basic characteristics we observe in the empirical data. So we determined the stress adjustment factor from a different set of simulations with magnitudes, again, 3 to 8, but at distances 1 kilometer for a variable stress parameter. Here we have the stress adjustment factor is calculated by this equation as a ratio of the simulations obtained for a given magnitude and stress parameter to the simulations at the same magnitude but the reference stress parameter. This figure shows the stress adjustments obtained from simulations, the ratio of the simulations, as a function of stress parameter for different periods, as shown in different panels. Each symbol represents different magnitude levels. As you can see, the stress adjustment has an increasing trend with increasing stress parameter and attains zero value at 100 bars by definition. The slope of this stress adjustment factors actually represent the strength of the stress parameter, the effect of stress parameter on the response spectrum or peak motions. So the steeper the data points, the stronger the effect on the response spectrum. As you can see, with increasing periods, especially the small magnitude events are less affected by the stress parameter because you are moving to the lower frequencies and crossing the high frequency range defined by the corner frequency. But for large magnitudes, we have the stress adjustment factor is less affected by the period up to 1 second, and they are strongly affected at 5 seconds because the corner frequency shifts to the lower frequencies with increasing magnitude. So stress has more effect on the response spectrum at a wider period range for large events compared to smaller events. So we modeled the stress adjustment by this equation here. This E delta sigma term, as I mentioned before, represents the rate of stress scaling. So it is the slope here. We model this E sigma term as a function of magnitude and period. So we have so far defined the source effect and geometrical spreading. And the other three terms are determined empirically. Fs, again, is borrowed from BSSA 14 model. So plugging if you want to adjust this generic GMPE to a specific region, you only need to plug the regional stress parameter, geometrical spreading, and analytic attenuation. And after that, you need to calculate the calibration factor needed based on the residuals between adjusted and the generic GMPE, between adjusted model and the empirical data in the target region. So we assume that magnitude, saturation, and site effects are transferable between regions. So as an example, we adjust this generic GMPE to Central and Eastern North America using the NGA East database. We consider earthquakes of magnitude larger than, equal, and larger than 3. This figure here shows the locations of epicenters from the selected events in the NGA East database. We consider both natural and potentially induced events. The squares here shows the potentially induced events, and circles are the natural events in the NGA East database. We select the ground motions up to 600 kilometers, and we exclude the ground motions recorded in the in the Gulf Coast region. So this figure shows the locations of the stations considered in this study. As you can notice, the stations are color-coded by their New York classification, and as you can see here, most of the New York A sites are located in Canada, and most of the New York D sites are located in this region. So we compile the PGA, PGV, and 5% damped PSA values from the NGA East database for the selected stations and earthquakes. This figure shows the magnitude distance distribution of the ground motion data compiled. Crosses represent the potentially induced events, and circles are for the natural events. So before calibration, before adjusting the generic GMPE, we correct the observed ground motions to equivalent New York BC site condition using the site effects model adopted from BSSA 14. As I mentioned before, the regional adjustment requires modifications to the attenuation and source parameters. So the geometrical spreading of Fourier amplitudes proposed for Central and Eastern North America by Atkinson and Boer is given by this equation. This is the same equation that we used in the generic GMPE, so we don't need to do any modifications to the Z term. We determine the regional analytic attenuation from the regression of the BC corrected motions based on this equation. Here, this FM term is the magnitude effect evaluated for the known magnitude from event I, and FZ term is the geometrical spreading determined for the known magnitude and distance for event I and station J. So we determine the gamma term here from the regressions. This EI term represents the average adjustment needed to match the observed amplitudes for event I. Its value can be attributed to two factors. First of this factor is the distance, the difference between the reference stress parameter that is carried by this FM function and its true value in the target region. And the second factor that's contributing to the EI term is the missing effects or different effects in the simulation. So as mentioned in the previous presentation, stress parameter is usually determined from matching the spectral amplitudes at short periods or high frequencies. Actually, this causes two problems. The first one is it gives non-unique solutions because of the trade-off between source and attenuation. Also, this limits the ability to calibrate the response spectral amplitudes at long periods because stress parameter has more effect at short periods, but it has limited effects at longer periods. So our approach is a little bit different than this conventional approach. We use we match the observed spectral shape rather than the spectral amplitudes to determine the stress parameter. This ensures a model calibration that is consistent over a wide period range. So it breaks off the trade-off between source and attenuation parameters and transfers all the overall amplitude differences to the calibration factor C. So we determine the stress adjustment, the stress parameter for each event by matching the spectral shape mapped into EI term with the spectral shape implied by F delta sigma term. So for each event, we try different stress parameters to match the spectral shape between these two terms by minimizing the standard deviation of residuals. So this figure shows the variation of stress parameters obtained from each event as a function of focal depth. As you can see, the stress parameters show an increasing trend with focal depth up to 10 kilometer, and their values roughly constant around 250 bars for the focal depth larger than 10 kilometer. The dash here, the hatchet, I don't know if you can see, but I'll mark a couple of them. The hatchet symbols represent the stress parameters obtained for the induced events or potentially flagged into induced events. So as you can see, they cluster about the average values, so they don't show distinct difference between distinct values compared to the stress parameters obtained from natural events. The diamond represents the average of stress parameter for all magnitudes. And when we look at the stress parameters in magnitude domain, we observe large variations at small magnitudes. This is because of the stress parameter is depth depending, and each here I color code the stress parameters for different depth ranges by different symbols and different color codes. The distinct separation of stress parameters as a function of depth is clearly seen here as well. And for magnitudes larger than 6, magnitudes larger than 5, we don't have much data, but generally, on average, the stress parameter is about 300 bars. So based on these observations, we model the regional stress parameter with this equation, which is both depth dependent and magnitude dependent, and lines shows their attributes in focal depth and magnitude domains. So this figures show the residuals between the best fitting stress parameter obtained for each event and its predicted value from the equation here. And diamonds again show the average residuals determined for evenly spaced focal depth or magnitude beams. As you can see, we don't observe any magnitude or depth-dependent trends, indicating that our stress parameter model working well for Central and Eastern North America. So, so far we determined the stress parameter for Central and Eastern North America. We know the geometrical spreading of Fourier amplitudes for the region, and we also determined the gamma term, the analytic attenuation for the region. So plugging these parameters, adjust the generic GMPE to Central North America, and the only remaining parameter that we need to calculate is the calibration factor based on the residuals between adjusted GMPE and the observed motions in the target region. So we calculate the average residuals for each event and plot them as a function of magnitude at different periods, as you can see in this figure. The diamonds show the average values, average event residuals for evenly spaced magnitude pins. Generally, the event residuals attain values less than 0. This is the residual. I should remind you that this is the residual remaining between the selected stress parameter, which was based on the spectral shape, and the actual amplitudes from the empirical data. So we don't see any magnitude-dependent trends. Generally, the event residuals are randomly distributed, and we don't see any distinct difference between natural or induced events. So this dashed line here shows the average event residual determined considering all magnitudes, and we define an event-based calibration factor based on, by taking the average of event residuals over all magnitudes. This figure shows the event-based calibration factor as a function of period. As you can see, the average value of the shaded area represents the standard error in this CE term, and the solid line is the average value over all magnitudes. As you can see, the CE term oscillates around -0.5 and 0 for periods up to 3 seconds, and after 3 seconds we have this increasing trend. This increasing trend can be due to the limited ability of stochastic simulations to generate the long period coherent motions in the empirical data. So after removing the event term from the residuals, we plot the average residuals for each station, as seen in this figure, as a function of VS30. The average residuals shown by rectangles here are about 0 value for NIHERP B and C sites, but NIHERP A site gives positive residuals, indicating that the ground motions are a little bit under-predicted by 15% on average, and NIHERP D sites show negative residuals, indicating that these sites are over-predicted. The ground motions on these sites are over-predicted by 20% on average. This may be actually because of the uneven distribution of the stations, as seen in this figure. If there is any slight difference in the attenuation rates, in between Canada, northern Canada, and Central North America, this may map into this residuals as seen here. So we don't see any evidence to correct the side effects or provide calibration for the side effects, and we assume that it is transferable to Central and Eastern North America. And finally, we correct the individual residuals for event and station terms and plot them as a function of rupture distance for different periods. Blue circles represent the residuals from individual residuals from natural events, and orange circles represent the individual residuals from induced events. At distances larger than 150 kilometers, the average residuals attain 0 values, but at closer distances, we have this decreasing trend. This trend may be attributed to the difference between the presumed path attenuation in the simulations, which was based on the Western North America data, and the true path attenuation in Central and Eastern North America. So we provide this calibration factor, the path calibration factor, which applies to the rate of attenuation at distances less than 100 kilometers. So after calibrating the adjusted GMPE, we here provide the overall look for the PSA predictions as a function of rupture distance for different magnitudes, from magnitude 4 to magnitude 8. The symbols here are shown for different magnitude ranges. The blue ones are magnitudes from 3.5 to 4.5, and orange ones are the magnitudes from 4.5 to 5.5. As you can see, our predictions are in good agreement with the observed data, and it also provides a seismological informed predictions for magnitudes larger than 6 where we don't have data. So overall, we provide median predictions for ground motions in Central and Eastern North America for average horizontal component PGA, PGV, and 5% depth PSA up to 10 seconds. For magnitudes from 3 to 8 at distances up to 600 kilometers for near BC site condition, and considering the regional stress parameters with depth and magnitude dependence. Thank you very much.
Thank you. So we'll leave one mic with this table. Is there a couple of questions? A question or two? Yeah, Jack Boatwright. Sahar.
If you go back 2 slides to your that one, it would really appear your model is under-predicting the fall off at long distances for these events as I understand what you said, the larger magnitudes. Is that correct for the orange?
The orange one?
Yeah.
This one? The red one? The line?
The orange versus the red. The red is your model. The orange is the empirical data.
That's right.
And it would appear as though your model is not falling off fast enough.
We would observe that here we don't have that residuals. We are like predictions giving 0 residuals on average for distances about 150 kilometers. I don't know if you can see from there the rectangles.
Yeah, this looks fine, but the other plot looks like a mistake.
This is because like I plotted here for a wide magnitude range. I don't know, like maybe I should put the average values here. I mean, yeah.
Okay.
Just one quick question. When you're extrapolating to high magnitudes, what's the stress? So you have an adjustment up to magnitude 5, right? That you calibrate.
I extrapolate the same stress factor, stress parameter for further magnitudes. So because we could only determine the stress parameter for magnitudes up to 6, and we just extrapolate it as a straight line.
Everything
so
above that is
constant. Yeah, for magnitudes larger than 5, it is 300 bars.
And in your reference model, it was 100 bars for all magnitudes. Is that right?
The generic GMPE, yes, it was 100 bars for all magnitudes. Yeah.
Just one comment, kind of. Linda, you have something? Okay. Just reinforcing what you said in response to Jack, you probably have more data at the lower end of that interval than in the upper end.
Probably.
So you expect some bias.
Yeah, actually, we can see it here. So it was like 4.5 to 5.5. So we have this gap.
Yeah. Okay.
That gives uneven distribution.
Right.
Yeah. Yeah.
Okay.
This is Linda. Why did you limit the model at 600 kilometers?
Because we thought that because we are using the empirical data to calibrate the generic GMP, right? So we can only obtain. We thought that this will be, the empirical data would be reliable up to 600 kilometers, and beyond that, it will be dominated by noise. That's why we limited up to 600 kilometers.
So for application, do you have a recommendation on if it would extrapolate to larger?
I didn't look at it. I should check it out.
I can just make a comment on that. It should extrapolate in a fairly well-behaved way because it's controlled by, the underlying model parameters.
John, raise your hand so Sahar.
John Stewart. So I got confused when you were talking about Fourier amplitudes versus response spectra. So at the end and at the beginning, too, you said it was response spectra, basically. But at several steps along the way, for example, I think when you were talking about the source and the geometric spreading terms, I thought you were talking about coefficients describing Fourier amplitudes. Was I mistaken about that?
Partially right. Maybe I should clarify it. Our geometrical spreading function has two components. The first component here, shown by Z parameter, represents the geometrical spreading of Fourier amplitudes. So when you switch to response spectrum domain, because of the response transfer function you apply in the response spectrum calculations, this may affect your attenuation rate. And this effect is represented by this second component here. So actually, the entire model is PSA-based, but we use the geometrical spreading of Fourier amplitudes and use this functional form to switch to response spectrum domain.
Okay. And then just another question related to that is these geometric spreading terms, minus 1.3 inside of 50, minus 0.5 beyond 50.
Yes.
That's for all frequencies?
Yes. It is just for the Z term, but this B3 and B4 terms are period dependent, and also it introduces magnitude dependence. So the overall attenuation is both magnitude and period dependent.
Okay, thanks.
Yeah, just to further just clarify on the points that were raised by John. Yeah, so that was in fact the purpose of breaking that function up into two parts was to capture this magnitude-dependent effect that you see in the response spectra, but not in the Fourier. So when you read the literature, you see all these models for geometric spreading in the Fourier domain that are independent of magnitude, and they're the simple, two-part things. So f of z is a response spectrum function, but we've chosen to break it up into two pieces so that we can separate the two effects.
Are you planning to scale it to 3,000 meters per second?
Actually, we preliminarily did that by using the site conversion factors from the white paper by Gale, which is based on the AB06 site amplification factors. So, yeah, we have already did that, but maybe we should a little bit work on it to give conversions for entire frequency range.
Yeah, it wasn't the 3,000. It wasn't really our primary focus. We wanted to sort of be going with the BC reference conditions so that we could map directly between the west and the east and have it all sort of be internally self-consistent. So the 3,000 meters a second wasn't really a primary focus. But.
Okay, thank you, Emra, very much. We're going to take a lunch break. If it's possible to make it a bit shorter so we come back on time and have time for discussions. So it's 12:15. Let's start at 1. You guys will hear noise because we'll test the phones, but please go grab food, tables in the back, and in the booth in the back, if you can raise the lights. Perfect. Wake up and enjoy your lunch. Okay, so can you unmute Bazad? Okay, Bazad, you should be unmuted now. So we're going to run a test, make sure we can hear you. So talk, please. Bazad, we don't see you talking. Please say talk. Nonsense, doesn't matter. Sing a song. Give that to Sifat.